Welcome, dear wanderer of the night. Thank you for finding your way here to this quiet corner of the universe where curiosity meets rest. This is the Sleepy Professor, a space carved out just for you, where learning feels like drifting, where facts settle gently into your mind like snowflakes finding their place on a winter evening. Tonight, we're going to explore chemistry together, not the frantic, intimidating chemistry of exams and lab coats, but the soft, beautiful chemistry that hums quietly all around you. The chemistry in every breath you take, in the warmth of your blanket, in the gentle glow of moonlight filtering through your window. Before we begin our slow descent into the molecular world, I wonder, where are you right now? Perhaps you're nestled in bed, your head sinking into a pillow that remembers your shape. Maybe you're curled up on a couch, wrapped in something soft, watching the day finally let go of you. Wherever you are, you're exactly where you need to be. If this is your first time here, it would mean the world to me if you could leave a like and subscribe. Each small gesture helps this gentle space reach other restless minds seeking calm. And to those of you who've returned, thank you. Your presence makes these midnight explorations feel less like lectures and more like conversations between old friends. You might also tap that notification bell, though I won't mind if you forget. The next video will wait patiently for you whenever you're ready to return. Now, I hope this isn't too interesting. I hope it doesn't keep you awake with wonder, though if it does, at least you'll drift off a little wiser than when you arrived. So settle deeper into wherever you are. Let your shoulders drop, feel the weight of your body supported completely, and hold this thought loosely in your mind as we begin. What if every color you've ever seen, every scent that's made you pause, every heartbeat that's carried you through your days, what if all of it could be traced back to the quiet, elegant dance of just a handful of tiny particles? The poetry of transformation. Chemistry is the story of change, beautiful, inevitable, endless change. It sits right there in the space between physics, the universe's rulebook, and biology, the living, breathing consequence of those rules. Chemistry is the bridge between the two, explaining why fire dances, why metal rusts slowly in the rain, why ice melts in your hand, why wounds heal, and why fireworks paint the night sky with impossible colors. It reveals, if you listen closely, how atoms, these impossibly small things, arrange themselves into water, into DNA, into the very air that's filling your lungs right now as you read these words. Humans have been practicing chemistry for as long as we've had hands to mix things with. Long before we knew what to call it, we were alchemists watching fire, grinding herbs, polishing metals, seeking patterns in how matter behaves. Those ancient seekers weren't wrong to chase the dream of turning lead into gold. What they discovered was something more valuable, the first glimpses into how everything transforms. Tonight, we'll wander together through the chemistry of everything, from the smallest atoms to the largest stars, from the bonds that hold molecules together to the reactions that power your very cells. You'll hear 300 carefully chosen facts, each one explained slowly, gently, clearly, each one another piece in this vast mosaic of matter. By the time we reach the end, whether you're awake or drifting in that pleasant space between waking and sleeping, you might see your world differently. Your body, your home, your planet, all of it woven from the same elegant chemistry. So breathe deeply. Let the day go, and let's begin this long, gentle journey into the quiet world of chemistry, the science that turns the ordinary into the extraordinary, the surprising spaciousness of everything. Here's a thought to make you feel simultaneously tiny and infinite. Almost everything around you, including you, is mostly empty space. Imagine that for a moment, the table beside your bed, the phone in your hand, the very atoms in your fingertips, they're surprisingly spacious. An atom's mass is squeezed into a nucleus so small it's almost unthinkable. Meanwhile, Electrons inhabit a diffuse cloud around it, a probability haze rather than a solid shell. If you could somehow enlarge an atom's nucleus to the size of a small seed and place it at the center of a sports stadium, the electrons would be whirling somewhere near the outer stands. Everything in between, open air, nothing but organized emptiness. That's how airy the foundations of the solid world truly are. And here's the thing. Those electrons don't circle the nucleus like planets on neat little tracks. That's the old comforting picture we used to draw. Instead, they occupy orbitals, regions of probability, places where an electron is likely to be found. It's a haze with rules, a map of likelihoods rather than a set of predictable paths. This ghostly probabilistic picture explains so much: why atoms can form bonds, why light gets absorbed and emitted in specific beautiful colors, why the table supporting your resting hand feels solid even though it's mostly organized space. At the heart of all that space sits the nucleus, packed with protons, and those protons decide identity. They're the passport that can't be forged. Count the protons, and you name the element. 1 proton means hydrogen, 2 means helium, 6 means carbon, 8 means oxygen. Change the proton count by even 1, and the entire element changes, the way a single digit in a phone number transforms who answers on the other end. This is the atomic number, the simplest label in chemistry, and the most decisive. Protons don't sit alone in there, though. Neutrons share the nucleus, adding mass and helping glue the structure together. They carry no electric charge, yet their presence is crucial. Vary the neutron count while keeping protons the same, and you create isotopes, versions of the same element with slightly different weights. Take carbon. Carbon with 6 protons and 6 neutrons. Carbon MOS12 is stable and common. Carbon with 6 protons and 8 neutrons. Carbon MOS14 is heavier and slowly decays, a quiet atomic clock that archaeologists use to date ancient wood and bone. Even water can carry subtle twists. Replace normal hydrogen with its heavier sibling deuterium, and the water still looks like water, yet it flows and freezes just a little differently. The chemistry stays familiar, but the rhythm changes. Now let's talk about those electrons, the lightweights of the atom. Electrons behave with strict restraint. They may only occupy certain energies, never anything in between. Imagine a staircase in the dark where your feet can land only on steps. Never hover mid-air. Give an electron just the right amount of energy, and it can hop to a higher step. Let it fall back, and it releases that exact amount, often as a photon of light. This quantized dance is why hot metals glow, why fireworks paint distinct hues across the night sky, and why stars carry barcodes in their spectra that reveal what they're made of. The pattern of allowed energies is unique to each element, turning every atom into a tiny instrument with its own set of notes. When you need to estimate how heavy an atom is, all eyes return to the nucleus. Protons and neutrons contribute almost all the mass. Electrons are so light that for most purposes their weight is a rounding error. Add up the protons and neutrons, and you have a good approximation of atomic mass. This simple arithmetic turns out to be powerful. It predicts how much a sample weighs, how much energy a reaction might release or absorb, and how much product you can make from given ingredients in a flask. It's the quiet bookkeeping that keeps chemistry honest. Yet the personality of an element, the way it bonds, reacts, and forms the stuff of life, belongs mostly to the electrons farthest from the nucleus, the valence electrons. These outermost electrons are the ones that meet other atoms at the border and decide whether to share, trade, or keep to themselves. Sodium has 1 valence electron and is eager to pass it on. Chlorine craves an extra electron and gladly accepts when sodium hands over its lone valence electron to chlorine. The result is a stable, neutral partnership we recognize as common table salt. Noble gases, with comfortably filled valence shells, are generally aloof, rarely bothered to react at all. Shift just one electron into or out of that valence shell, and the change in behavior can be dramatic. That's why rows and columns in the periodic table carry patterns. Elements in the same column share similar valence arrangements, and often act like relatives at a reunion, different in details, similar in temperament. So the atom story is threefold: a dense, tiny center that sets identity and weight, a set of neutrons tuning stability, and a faint, rule-bound cloud of electrons that writes the script of chemical behavior. From these simple parts, protons, neutrons, and electrons arise all the colors in a flame: the rust on iron, the fizz of a drink, and the breath moving in and out of your chest right now, gentle and steady. Chemistry begins here, in the mostly empty space that somehow builds a world. The nucleus, nature's strongest glue. Picture the atom as a softly lit sphere with nothing truly solid to touch. Most of its size is the electron cloud, and that cloud is a map of likelihood, not a shell you could peel away. An orbital says, the electron is likely to be found here, the way a weather map says rain is likely in a certain region. Sometimes the electron is closer in, sometimes farther out, sometimes in lobes that look like balloons or clover leaves, but it's always about probability. This is why the word cloud fits so well. It's real, measurable, and patterned, yet never a rigid surface. Held at the center is the nucleus, a dense knot of protons and neutrons packed together by the strong nuclear force. Now, protons would normally repel one another. Positive charges push apart, but at extremely short distances, the strong force overwhelms that repulsion and binds them tightly, with neutrons boosting the stability of the arrangement. Think of it as the most powerful glue nature uses, working only when particles are almost touching. Without this intimate, short-range force, nuclei would fly apart, and the periodic table would collapse into a drift of lonely protons. The labels we give elements carry stories from languages long traveled. Atomic symbols are often short and familiar. C for carbon, O for oxygen, but some wear their history on their sleeve. No comes from natrium, K from kalium, Fev from ferrum, the Latin word for iron. These symbols form a compact chemistry alphabet that lets equations stay crisp and universal across languages. Whether you're reading a textbook in English, Spanish, or Japanese, Pho still points to the same tough silvery metal that built railways and bridges. To compare the masses of atoms cleanly, chemists agreed on a tidy yardstick, the unified atomic mass unit. It's defined so that one atom of carbon-12, carbon with 6 protons and 6 neutrons, weighs exactly 12 units. Everything else is measured relative to that. Hydrogen comes in at just about 1 unit. Oxygen settles near 16. You don't need to memorize the decimals to get the point. This definition is like setting the scale 0 in the size of each tick mark, so everybody's measurements line up. When atoms change their charge, they do it the easy way by moving electrons, not by rearranging the nucleus. Ionization is the process of turning a neutral atom into an ion by losing or gaining electrons. Strip an electron away, and the atom becomes positively charged. Tuck an extra electron in, and it becomes negatively charged. The proton count inside the nucleus doesn't budge during ordinary chemistry, because changing that would mean nuclear reactions, not everyday bonds and solutions. In the gentle realm of beakers and batteries, it's the nimble electrons that shuffle, not the anchored protons. From that simple shuffle come 2 families with opposite personalities. Lose electrons and you get cations, positively charged species. Gain electrons and you get ananynes, negatively charged species. If you like mnemonics, Remember, cations are positive. Sodium tends to become a cation with a single positive charge, written nawa. Chlorine prefers to become an anion with a single negative charge, written cholera. When they meet, their opposite charges pull them together into sodium chloride, better known as table salt. In water, those ions separate and move freely, which is why salty solutions conduct electricity so well. The world of charge is courteous and predictable. Opposites attract, like charges repel, and the dance of ions quietly powers nerves, batteries, and the chemistry of life. Isotopes, siblings in the same family. Isotopes are like siblings in the same family. They share the same number of protons, so their chemical personalities match, but they carry different numbers of neutrons, so their masses differ. That small change in weight can lead to gentle shifts in behavior. Swap ordinary hydrogen, prosium, for its heavier sibling, deuterium, and you get heavy water. It still looks like water and splashes like water, but it freezes, boils, and flows just a little differently because each molecule is quite literally heavier on its feet. Chemically familiar, physically distinct. That's the quiet charm of isotopes. One isotope, carbon-14, carries a built-in clock. It forms high in the atmosphere and ends up in living things, joining the carbon already in their tissues. While an organism is alive, the ratio of carbon-14 to carbon-12 stays steady. After it dies, the carbon-14 slowly decays, tick by tick. By measuring how much remains, scientists can estimate the time since death, not to the exact day, but well enough to place artifacts, wood, or bone within tens of thousands of years. It's a dating method written by the atom itself, a gentle glow that fades on a schedule. Some isotopes are chosen for their helpful signals inside the body. In hospitals, technetium-99, the MER, stands for metastable, is a favorite because it emits photons that cameras can detect while delivering a relatively low radiation dose. Attach it to a compound that targets a particular organ, and physicians can watch blood flow, bone turnover, or heart function in real time. The isotope is the tracer. Biology provides the map. The moment it has done its job, it decays to a more stable form, and the image becomes a record of the body's chemistry at work. Stable isotopes tell stories at a planetary scale. Take oxygen-18 and oxygen-16. Water molecules containing the heavier oxygen-18 evaporate and condense just a bit differently than those with oxygen-16. Over seasons and millennia, that tiny preference is captured in snow layers that turn into ice, and in the shells of ancient marine organisms. By measuring the oxygen-18 to oxygen-16 ratio in an ice core or a fossil shell, scientists can reconstruct past temperatures and rainfall patterns. It's like reading Earth's diary, where every page is written in oxygen's subtle handwriting. Behind these signals is a simple physical tendency called isotopic fractionation. Lighter isotopes move, vibrate, and diffuse a little faster. They're slightly more likely to evaporate first, to zip through membranes, or to take part in reactions that favor speed. Heavier isotopes lag just a hair behind. In a single glass of water, the difference is invisible. Across oceans, ice sheets, and ages, the pattern becomes clear. Nature separates the nearly indistinguishable, and the separation turns into a clue. At the heavy end of the chart, uranium offers a different lesson. Uranium-235 is fissile, meaning that when it absorbs a neutron, it can split into smaller nuclei, releasing energy and more neutrons that can keep the process going. A chain reaction. Uranium-238 is far more abundant in natural uranium, but it's less reactive in that way. It doesn't readily sustain a chain reaction. That contrast, scarce but eager versus common but reluctant, underpins how nuclear reactors are fueled and how enrichment works. One isotope is the match, the other is the pile of wood. Together they remind us that changing only the neutron count can reshape the possibilities of an element, from dating ancient charcoal to lighting modern cities. Radioactive decay has a calm predictability to it. It follows first-order kinetics, meaning the rate at which a sample decays is directly proportional to how much of it is present. The key idea is the half-life, the time it takes for half the atoms in a sample to transform into something else. After one half-life, half remains. After two half-lives, 1/4. After three, 1/8. The clock doesn't speed up or slow down with temperature or pressure the way ordinary chemical reactions do. Each nucleus keeps its own quiet schedule, and large crowds of them add up to a smooth statistical fade. Not all decays look the same. In alpha decay, a nucleus emits a compact bundle, 2 protons and 2 neutrons, essentially a helium-4 nucleus, which carries a positive charge and can be stopped by a sheet of paper or even the outer layer of skin. Beta decay changes identity inside the nucleus. A neutron can turn into a proton with the emission of an electron and an antineutrino beta minus, or a proton can become a neutron with the emission of a positron and a neutrino beta plus. Gamma decay emits no particles at all, just a photon of high-energy light as the nucleus relaxes from an excited state to a lower one. Think of alpha as a little fragment leaving, beta as a swap of identity inside the nucleus, and gamma as the release of leftover energy. That positron mentioned in beta plus decay isn't just a theoretical guess, it's the star of PET scans, short for positron emission tomography. Doctors attach a positron-emitting isotope to a molecule that cells naturally take up, often something akin to glucose. When the isotope decays, the emitted positron quickly meets an electron, and the pair annihilates, producing 2 photons that fly off in exactly opposite directions. Detectors catch these paired flashes, and computers reconstruct a map of metabolic activity, right where cells are ravenous for fuel, dim where they're quieter. In this way, PET turns atomic whispers into images that guide diagnosis and treatment. Sometimes radioactive atoms drift where we live. Radon is a noble gas that seeps from soil and rock as heavier elements decay underground. Being a gas, it can slip into basements and accumulate in still air. Outside, it disperses. Indoors, it can build up, and its decay products can lodge in lungs. Because radon is colorless and odorless, it's usually found only by testing, and ventilation is the simple, effective remedy. It's a reminder that radioactivity is a natural part of Earth's chemistry, one that calls for informed caution rather than panic. On the timescale of Earth itself, radioactive decay writes the planet's calendar. Uranium-238, the most abundant uranium isotope, decays through a long chain of steps until it becomes lead-206, which is stable. Minerals trap uranium when they form, and as the uranium decays, lead accumulates in a predictable ratio governed by uranium's half-life. Measure the amounts of parent and daughter, and you can calculate a formation age for the mineral. This uranium clock has dated some of the oldest rocks on the planet, and even helped set lower bounds on the age of Earth itself. Isotopic labeling is a gentler trick that chemists use to follow atoms through complicated reactions. Replace a common atom with a harmless isotope, oxygen PN instead of oxygen-16, deuterium instead of procyon, carbon-13 instead of carbon-12, and you can trace where that specific atom goes without changing the overall chemistry very much. In a reaction with many moving parts, the labeled atom is a tiny flag. Spectrometers and other instruments can see the flag even when human eyes cannot, revealing mechanisms step by step. Which bond breaks first? Which intermediate forms? Where did the oxygen in a product originally come from? It's cartography for molecules, mapping their journeys with just a small nudge to their mass. Let your breathing slow. Feel your eyelids grow heavier. The atoms we're describing are invisibly small, yet they govern everything from the stars overhead to the pillow cradling your head. Electrons, the quiet architects. Electrons arrange themselves in atoms by climbing a ladder of energy, choosing the lowest available rungs first. This general pattern is called the Aufbau principle, building up. Imagine filling seats in a theatre from the front row to the back. The best seats go first, and only when a row is full do people move to the next. In atoms, the rows are orbitals, each with a set capacity and energy. The order isn't simply 1, then 2, then 3 by shell number, because of subtle interactions between the nucleus and the shapes of orbitals. The 4s orbital fills before the 3 days, and similar quirks appear throughout the table. Still, the guiding idea stays simple. Electrons prefer lower energy, and they only climb higher when the comfortable places are taken. There's also a strict rule about sharing those seats. The Pauli exclusion principle says that no two electrons in the same atom can have the exact same set of quantum addresses. In practical terms, this means that an individual orbital can hold 2 electrons at most, and if it holds 2, their spins must oppose each other. One points up, the other down, balancing like tiny bar magnets arranged north to south. This paired arrangement reduces repulsion and keeps the bookkeeping neat. Without the Pauli rule, electrons would have no reason to spread out, and the periodic table with all its orderly patterns would unravel. When orbitals of the same energy are available, electrons act a bit like polite guests at a party. They spread out before they start to pair up. This is Hund's rule. If you have, say, 3p orbitals at the same energy, an electron will sit alone in each orbital with parallel spin before any orbital receives a second opposite spin electron. The effect minimizes electron-electron repulsion and stabilizes the atom. It also explains why certain electron configurations are particularly steady, half-filled or completely filled sets of orbitals offer a kind of symmetry and balance that nature quietly prefers. To keep track of capacity, it helps to know the simple head counts. The subshell has 1 orbital and can hold 2 electrons. The p subshell has 3 orbitals and can hold 6 electrons. The d subshell has 5 orbitals and can hold 10 electrons. The fifth subshell has 7 orbitals and can hold 14 electrons. Those numbers, 2, 6, 10 and 14, come straight from the number of orbitals multiplied by 2 spins. This tally is more than trivia. It sets the rhythm of the periodic table. As you add electrons across a period, you fill p orbitals one by one, drop to a new block, and you may begin to fill d or f orbitals with their larger capacities and more intricate shapes. While the whole electron arrangement matters, the personality of an element shows up most clearly in its outermost electrons, the valence electrons. These are the electrons that meet other atoms, form bonds, and decide whether a substance is inert, reactive, acidic, basic, metallic, or non-metallic. Elements in the same column of the periodic table tend to have the same number of valence electrons, which is why sodium, potassium, and cesium behave like cousins with similar habits. Change the valence count by even 1, and the chemistry can swing from explodes in water to barely reacts at all. Valence electrons are the negotiators at the border, arranging trades, sharing pairs, or standing aside. Transition metals are a special showcase for how electron configuration shapes behavior. In these elements, the d subshells are being filled, and those d electrons sit close in energy to the cell electrons of the outer shell. Because their energies are similar, transition metals can lose different numbers of electrons under different conditions, leading to varied oxidation states. Iron can be felzered or felzered, copper can be felzered or felzered or felzered, copper can be felzered or felzered. This flexibility is one reason transition metals make excellent catalysts. They can switch electron counts and coordinate with different partners without tearing themselves apart. The partially filled d orbitals also allow interesting geometries and colorful complexes, as incoming ligands interact with the d electrons and split their energies, producing vivid shades in solution. Put these ideas together and a pattern emerges. Electrons fill the lowest energy orbitals first, never duplicating a full set of quantum details. They spread out across equal energy seats before pairing. The capacities of sols, p, d, and φ subshells set the structure of the periodic table. The outermost electrons dictate reactivity, and the d-electron playground of the transition metals opens a world of flexible oxidation states and catalysis. From these compact rules flows the grand variety of chemical behavior, from the passivity of noble gases to the lively colors of metal complexes, and the reliable bonds that build life's molecules. Your breathing is slower now, isn't it? Let each fact settle gently, like layers of sediment forming rock over centuries. There's no rush, we have all night. Noble gases, the contented neighbors. Noble gases sit on the far right of the periodic table, like contented neighbors who already have everything they need. Their valence shells are full, no incentive to trade or share electrons, so they mostly ignore the chemical bustle around them. Helium, neon, argon, they are the wallflowers of chemistry, and their calmness is a direct consequence of electronic completeness. A filled outer shell is a finished puzzle, satisfying, symmetrical, and not looking for extra pieces. Every good rule in chemistry has a few elegant wrinkles, and chromium and copper are classic examples. Their ground-state electron configurations borrow a little stability by achieving half-filled or fully filled d subshells. Chromium prefers to be written as R-force 4 3DNR rather than R-force 4 3DNR, because a half-filled set of 5d orbitals with one electron each is especially stable. Copper leans toward a 4-3 3D line, favoring a completely filled d subshell. These choices reflect tiny energy trade-offs that pay dividends in stability, reminding us that electrons are accountants of energy first, rule followers second. When atoms form ions, the departing electrons usually come from the highest principal energy level, not necessarily from the last subshell we wrote when filling. That's why many transition metals lose their 4s electrons before touching their 3d electrons. The 4s electrons, though filled earlier, sit at a slightly higher principal level and are more easily removed when the atom becomes a cation. It's a subtle ordering. Fill and remove are not mirror images, and chemistry cares about the energy right now, not the historical path the electrons took to get there. As you move across a period from left to right, the effective nuclear charge felt by the valence electrons increases. The nucleus gains protons, but the inner shielding doesn't increase enough to cancel that extra pull, so the outer electrons are drawn a little closer. Radii shrink, ionization energies rise, and electronegativities climb. That steady strengthening of attraction helps explain why fluorine is so keen to attract electrons, while sodium, just a few steps away, is happy to let one go. Shielding is the counterbalance to that pull, the way inner electrons blunt the full charge of the nucleus from the perspective of the outer ones. Electrons in lower shells spend more time close to the nucleus, and their negative charge repels outer electrons, reducing how strongly those outer electrons are attracted to the nucleus. More inner electrons generally mean more shielding, which is one reason atoms grow larger as you go down a group. The nucleus gets stronger, but the layers of electron insulation thicken too, letting the outer shell sit farther out. Underneath all these rules sits a mathematical heartbeat. Atomic orbitals are not little tracks, but solutions to the Schrödinger equation, functions that describe the probability of finding an electron in space. The familiar shapes, the sphericals, the dumbbell-shaped P, the more intricate T and F, are pictures of where the electron is likely to be found, not where it must be. Nodes, lobes, and phases emerge naturally from the mathematics, and those features ripple outward into real-world behavior, bond angles, colors of metal complexes, even the hardness of minerals. The poetry of electron configuration is written in equations, but it's read in the colors of fireworks, the stability of noble gases, and the quiet way atoms decide who they will bond with and who they will politely ignore. Let that image rest in your mind as your body grows heavier. Atoms deciding, electrons negotiating, the whole periodic table, a conversation written in charges and distances. Periodic trends, the landscape of elements. Slide your finger across a period of the periodic table from left to right, and atoms quietly pull themselves inward. The effective nuclear charge rises as protons are added to the nucleus, but shielding from inner electrons doesn't increase enough to cancel that pull. Valence electrons are drawn closer, so atomic radius generally shrinks across a period. Now trace downward in a column, and the trend flips. New shells are added, shielding increases, the outer electrons sit farther from the nucleus. Atomic radius grows as you move down a group, giving cesium a much roomier electron cloud than lithium. That tightening across a row and loosening down a column explains a twin trend in ionization energy, the energy needed to remove an electron. When electrons are held closer and more tightly, prying one loose takes more effort. Ionization energy generally increases across a period and decreases down a group. Helium hangs on with determination. Hesium lets go with a shrug. There are small bumps and dips caused by subshell structures. Pulling the first electron from a full or half-full subshell can cost a bit more, but the broad sweep is clear. Compact atoms cling, spacious atoms share. A related measure, electron affinity, tracks the energy change when a neutral atom gains an electron. As you move across a period, atoms are usually more eager to accept an extra electron to complete or approach a filled valence shell. So electron affinities tend to become more negative, meaning more energy is released. The pattern isn't perfectly smooth because orbital shapes and electron-electron repulsions introduce local quirks. For example, filling a p orbital that's already half full can sometimes be less favorable than expected. Still, the idea holds atoms that are already pulling their electrons close, often welcome one more with a satisfying snap. Electronegativity ties these ideas together in the context of a bond. It's a comparative scale of how strongly an atom attracts shared electrons when it's covalently bonded. Across a period, electronegativity increases as atoms become smaller and nuclear pull grows. Down a group, it decreases as distance and shielding weaken the grip. At the top of this scale sits fluorine, the champion of electron tug-of-war. Give fluorine an opportunity to share, and it pulls the shared pair toward itself, polarizing the bond. This simple gradient from low electronegativity metals on the left to high electronegativity non-metals on the right helps predict which bonds are mostly ionic, which are polar covalent, and which are nearly non-polar. All of this plays into metallic character, the broad set of behaviors associated with metals, a willingness to lose electrons, formation of positive ions, and the capacity to conduct heat and electricity. Metallic character increases as you go down a group and decreases as you move across a period. Sodium, magnesium, aluminum, each step to the right, softens the metal's readiness to donate electrons, and by the time you reach silicon and phosphorus, the character has shifted toward metalloids and nonmetals. Head down a column though, and the atoms grow larger, their outer electrons held more loosely, restoring that easy electron donation that metals are known for. You may notice that noble gases often don't appear on electronegativity charts. There's a simple reason: they rarely form bonds at all, so assigning them a value on a bonding-based scale can be misleading. Their filled valence shells make them largely uninterested in sharing electrons, which means there's not much real-world data to anchor a number. In exceptional conditions, some noble gas compounds do form, especially with xenon, but for everyday chemistry, the noble gases sit out the tug of war, and the scale focuses on the players who actually take the field. Put the map together, and the periodic table becomes less a list and more a landscape. Radii shrinking across, swelling down, ionization energies rising across, falling down, electron affinities growing more exothermic across, with gentle exceptions, electronegativities peaking at fluorine and fading toward the corners, metallic character blooming down the left side and withering toward the upper right, noble gases watching calmly from the sidelines. With these contours in mind, trends stop being facts to memorize and start becoming features you can navigate, predicting how unfamiliar elements will behave long before you meet them in the lab. Your eyelids are heavy now. Let the periodic table spread out in your mind like a quiet map, each element finding its place, each trend a gentle slope you can follow without effort. The personality of groups. Group 1, the alkali metals, are the sprinters of reactivity. Give them water, and they leap into action, each atom eager to lose its single valence electron and become a +1 cation. The result? A hydroxide solution and a puff of hydrogen gas that can ignite if the reaction runs hot enough. In simple stoichiometry, 2 Nas 2 ace tho, oso 2 Nas o co, Ars o co. Lithium tends to fizz politely. Sodium zips along. Potassium, rubidium, and cesium can turn downright theatrical. The underlying reason is straightforward. As you move down the group, the outer electron sits farther from the nucleus and is more easily removed, so the reaction gets faster and more exothermic. Next door in group 2, the alkaline earth metals prefer a measured pace. They commonly form +2 cations by shedding 2 valence electrons, landing in the comfortable stability of a noble gas-like configuration. They're less reactive than their group 1 neighbors, because losing 2 electrons takes more energy than losing 1. Magnesium and calcium react with water, but usually more slowly, and often require heat or finely divided surfaces to get going. Their hydroxides are less soluble across the group, which is why magnesium hydroxide shows up as a milky antacid, and calcium compounds build seashells, limestone, and the sturdy backbone of concrete. Group 17, the halogens, are chemistry's avid collectors. With 7 valence electrons, they're one short of a filled shell and very keen to complete it, which makes them highly reactive nonmetals. Pair a halogen with a metal and you get a salt, a neat ionic lattice born from electron transfer. Sodium plus chlorine forms sodium chloride. Calcium plus bromine forms calcium bromide. Down the group, reactivity softens a bit as atoms grow and the added electron sits farther out, but the appetite for that final electron remains. In elemental form, they span phases and colors: pale green chlorine gas, red-brown bromine liquid, deep purple iodine solid, yet they all share the same craving for completion. On the far right, the noble gases often watch the action from a polite distance, but even the quiet ones have their adventurous days. Under extreme conditions, powerful oxidizers, high pressures, or excited states, heavier noble gases can form compounds. Xenon is the standout, bonding with fluorine to make xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. These are stable enough to bottle and study, proof that unreactive in chemistry usually means unreactive under ordinary conditions. The heavier the noble gas, the more its outer electrons are polarizable, and the more likely unusual bonds can form when pushed. Transition metals are the nimble multitaskers of the table. With d subshells close in energy to their outer electrons, they can adopt multiple oxidation states and coordinate to a changing cast of ligands. That flexibility, switching electron counts, binding and releasing partners, stabilizing different intermediate states, is exactly what a good catalyst needs. Iron can cycle between Fe-Herden. Manganese marches through a whole parade. From Mansfeith up to Manfei-Herden, palladium shuffles between oxidation states as it stitches carbon chains together in coupling reactions. Because catalysts are not consumed, a pinch of the right metal complex can steer a reaction down a smoother path, lowering the activation energy and boosting yield without rewriting the final recipe. Tucked beneath the main body of the table, the lanthanides form a close-knit family of F-block elements with remarkably similar chemistry. Their valence behavior is dominated by a +3 oxidation state, and their F electrons are largely shielded, so they don't vary wildly from one neighbor to the next. That sameness made them notoriously tricky to separate historically, but it also gives them a suite of shared talents, strong magnetic moments, sharp spectral lines, and a knack for phosphorescence. Europium brings the red to television and phone screens. Terbium lights up green. Neodymium lends magnets their muscle in compact motors and headphones. Subtle differences in ionic radius, the lanthanide contraction, as the series progresses, fine-tune their coordination chemistry, but the headline remains similar size, similar charge, similar behavior, especially as +3. Seen together, these groups sketch the table's personality. Alkaline metals eager to give one electron, alkaline earths calmly handing over two, halogens hungry to take one back, noble gases mostly content but capable of surprises, transition metals acting as adaptable catalysts, lanthanides humming along in +3, lighting up technology and sharpening images with their spectral signatures. The periodic trends aren't just arrows on a chart, they're habits written by electrons, predicting who reacts with whom, how fast, and to what end. Take a slow breath. Feel how your body has settled. These elements, these patterns, they're in everything around you, in the air, in the water, in the very cells of your fingertips resting on the blanket. Ionic bonding, the pull of opposites. Ionic bonding is the quiet pull between opposites. A metal atom that easily lets go of an electron becomes a positively charged cation. A nonmetal that eagerly accepts that electron becomes a negatively charged anion. Place them near each other, and electrostatic attraction does the rest. You can picture it in steps. Sodium solid gives up one electron to become Naur. Chlorine gas accepts one electron to become chlorine. Then Naur and chlorine assemble into a neutral crystal of sodium chloride. The bond is not a shared pair like a covalent handshake. It's the persistent tug of unlike charges holding a lattice together. The firmness of that lattice is captured by lattice energy, the energy released when gaseous ions pack into a solid. Smaller ions can get closer, and higher charges tug harder, so both of those raise lattice energy. Magnesium oxide, with Mg and O und Vil, binds far more tightly than sodium chloride with +1 and 1 pole. That's why magnesium oxide has a much higher melting point. Stronger attractions mean more heat is needed to pry the ions apart. In short, the more compact and more highly charged the ions, the sturdier the ionic solid. Ionic solids are full of charges, yet a cool, intact crystal won't carry electricity through itself. The ions are locked in place, unable to move as charge carriers. Melt the crystal, however, and the ions are free to drift. Dissolve it in water, and the ions separate and swim. In either case, mobile charged particles are available, and the liquid conducts. This simple switch, fixed in a solid free in a melt or solution, is why table salt doesn't conduct on your shelf, but salty water lights up a conductivity probe. That rigid arrangement also explains why many ionic compounds are brittle. Press on a crystal, and if layers slip just enough, rows of like charges can be forced to face each other, positive against positive, negative against negative. Repulsion spikes and the crystal cleaves along a plane. Instead of bending like a metal, the ionic lattice snaps. The neat flat faces of salt crystals are the geometric fingerprints of that ordered yet fragile arrangement. Water can unravel these lattices because it hydrates ions, surrounding them with oriented molecules that stabilize the charges. Ion size and charge density tip the balance between lattice energy, which holds ions together, and hydration energy, which pulls them apart. Small, highly charged ions have intense electric fields and attract snug, structured shells of water. Large, diffuse ions interact more gently. When hydration energy outweighs lattice energy, the salt dissolves readily. That's why sodium nitrate dissolves easily, while some sparingly soluble salts like barium sulfate resist. Their lattices are simply too strong to be compensated by hydration. Among the ions that roam in water, oxygens are especially common. These are polyatomic anions with oxygen atoms bonded to a central nonmetal, and their structures often spread negative charge through resonance, which stabilizes them. Nitrate, nothrive, and sulfate. So thive, nothar are classic examples. Their oxygen frameworks make them versatile partners in chemistry, from plant nutrition to atmospheric processes, because the negative charge is shared across several atoms. Oxygens are generally quite stable in solution, and form a wide variety of salts, some highly soluble, some stubbornly not, depending on how their charge and size match up with the cation. Let your mind rest on that image. Ions dancing in water, each one wrapped in its own shell of oriented molecules, drifting through solution like guests at a molecular ball. Covalent bonding, the shared story. A covalent bond is a shared story between atoms. Instead of handing electrons over, they hold a pair between them. The strength of that partnership depends on bond order, how many shared pairs there are. A single bond shares one pair. A double bond shares two. A triple bond shares three. As bond order increases, the bond usually grows stronger and shorter. Carbon-carbon single bonds are longer and easier to stretch than carbon-carbon triple bonds, which are compact and tough, like a tightly drawn rope compared with a loose cord. This simple ladder, single, double, triple, is one of the most reliable guides to how rigid or flexible a molecule will be. Under the hood, those shared pairs live in overlapping orbitals. A sigma bond is the head-on overlap of orbitals, along the line between the two nuclei, the simplest, most direct connection. A pi bond is different. It forms from the side-by-side overlap of p orbitals above and below the bonding axis. Every single bond is a sigma bond. A double bond contains one sigma plus one pi. A triple bond contains one sigma plus two pi. Think of sigma as the backbone and pi as the reinforcing beams that add strength and shape. Because pi bonds are formed by that side-locking of electron clouds, they resist twisting. A single bond, just sigma, can rotate fairly freely at room temperature. Groups can spin around that axis like beads on a string. Add a pi bond, and rotation becomes restricted. Twist too far, and you'd have to break the pi overlap. That's why alkanes can have distinct E and Z or cis and trans arrangements. The double bond freezes parts of the molecule into place. This rigidity shapes everything from the scent of molecules to the colors of dyes and the behavior of biological membranes. Not all shared pairs are shared equally. Bond polarity arises when one atom pulls on the shared electrons more strongly than the other. The measure of this tendency is electronegativity. A large difference means a more polar bond, with electron density shifted toward the more electronegative partner. In a hydrogen-fluorine bond, the electrons huddle closer to fluorine, giving it a partial negative charge and leaving hydrogen with a partial positive. Stack many polar bonds in a molecule, and their directions matter. Sometimes the polarities cancel, sometimes they reinforce to create a strongly polar molecule that mixes well with water and interacts keenly with ions. Resonance adds a layer of elegance to this picture. Some molecules cannot be well described by a single drawing of bonds and lone pairs. Instead, electrons are delocalized across multiple positions, and several contributing structures, resonance forms, blend into a more accurate hybrid. Nitrate, no CIR, is a classic example. The negative charge and the pi bonding are spread evenly over the three oxygens, making all nitrogen-oxygen bonds equivalent in length and strength. Benzene's ring is another. The pi electrons circulate over the entire hexagon, producing equalized carbon-carbon bonds and an extra measure of stability known as aromaticity. Resonance isn't electrons jumping back and forth. It's a way of acknowledging that electrons are shared over a broader canvas. For many main group molecules, the octet rule offers a tidy goal. Atoms often arrange themselves so that each has 8 electrons in its valence shell. It's a helpful guide, but it's not a law. Some molecules have expanded octets because their central atoms can access d orbitals and accommodate more than 8 electrons. Phosphorus pentachloride and sulfur hexafluoride are straightforward examples. Phosphorus and sulfur sit in environments where 5 or 6 bonding pairs can be held stably. On the other side, electron-deficient molecules make do with less than an octet. Boron trifluoride famously stops at 6 valence electrons around boron, yet it's a stable compound under ordinary conditions. In between lie radicals, with unpaired electrons and odd electron counts, and hypervalent ions that stretch the bookkeeping in polar environments. The octet rule is best treated as a compass, not a cage. It points in the right direction most of the time, while chemistry keeps a few scenic detours for special cases. Put together, these ideas make covalent bonding feel both intuitive and rich. Shared pairs that tighten with higher bond order, sigma backbones and pi reinforcements. Double bonds that lock shapes and create geometric isomers. Electronegativity pulling charge to sculpt polarity. Resonance spreading electrons for stability. Octet guidelines that bend gracefully when the energy landscape allows. From the fragrance of an orange to the strength of Kevlar and the base pairs of DNA, this is how atoms cooperate to build the textures, colors, and structures of the world. Your body is sinking deeper now, each breath a little slower, each thought a little softer. These bonds, these quiet partnerships between atoms, they're holding you together right now as you rest. Molecular shapes, the dance of electrons. Molecules choose their shapes by giving their electrons some personal space. That's the simple wisdom of VSEPR, valence shell electron pair repulsion. Around a central atom, regions of electron density, bonding pairs and lone pairs arrange themselves as far apart as possible to minimize repulsion. Count the regions, spread them out symmetrically, and you have the basic geometry. Attach the atoms to those regions, and the shape appears. With 2 regions, you get a straight line. With 3, a flat triangle. With 4, a 3-dimensional tetrahedron. It's a tidy rule of back off a bit please, played by electrons. Not all electron pairs push equally hard. Lone pairs, electron clouds that belong to the central atom alone, repel more strongly than bonding pairs that are shared between atoms. That extra shove squeezes nearby bond angles slightly. Water is a classic example. Its electron geometry is tetrahedral, but because two of those positions are lone pairs, the HOH angle compresses below the comfortable tetrahedral angle, and the molecule becomes bent. Ammonia shows the same idea in 3 dimensions: 3 NH bonds and 1 lone pair, arranged tetrahedrally in electron terms, but the shape you see is trigonal pyramidal, with slightly pinched angles, because that lone pair elbows the bonds a little closer together. From that logic, a short gallery of common shapes follows. 2 regions make linear molecules like carbon dioxide, where electron clouds sit opposite each other. 3 regions make trigonal planar molecules like boron trifluoride, flat and evenly spaced. 4 regions give tetrahedral molecules like methane, a shape that spreads bonds to the corners of a pyramid with a hidden center. 5 regions create trigonal bipyramidal structures, like phosphorus pentachloride, with 3 bonds around the equator and 2 at the poles. 6 regions produce octahedral molecules like sulfur hexafluoride, where 6 identical positions radiate from the center like spokes on a perfect wheel. Each geometry is just the most peaceful way to sit when everyone wants elbow room. Whether a whole molecule is polar depends on 2 things at once: the polarity of the individual bonds and the way those bonds are arranged in space. Carbon-oxygen bonds are polar, for example, but in carbon dioxide they point in opposite directions and cancel each other, leaving a non-polar molecule. In water, the 2 polar OH bonds are not arranged in a line, they meet at an angle, and their polarities reinforced to give the molecule a permanent dipole. That's why water loves to dissolve ions and other polar substances. Geometry doesn't simply decorate a molecule, it decides how charges add up or cancel out. Hybridization offers another lens to make sense of these shapes and the equal bonds they contain. In methane, carbon mixes 1 s orbital with 3 p orbitals to form 4 equivalent sepal hybrids, each pointing toward a corner of a tetrahedron. That's why all 4 CH bonds are identical and evenly spaced. In Athena, carbon uses sepiquadrat hybrids to form a flat trigonal arrangement, with 1 unhybridized p orbital left over. Those 2 p orbitals overlap side by side to make a p bond, locking the double bond and restricting rotation. In ethine, carbons use sipping hybrids to line up in a straight line, with 2 perpendicular p orbitals on each carbon forming 2 pi bonds for a triple connection. The hybrid story is a convenient way to explain why bonds that look the same really are the same. Delocalization brings a special kind of calm to certain molecules, especially aromatic rings. In benzene, the 6 carbon atoms form a hexagon with alternating single and double bonds in a simple drawing, but the electrons that make those pi bonds are actually spread evenly around the ring. The result? All carbon-carbon bonds become equal in length and strength, somewhere between a single and a double bond. This shared circulating electron cloud grants unusual stability, aromatic stability, and gives rise to distinct reactivity and characteristic spectroscopic fingerprints. You see the effects in everything from the fragrance molecules of essential oils to the pigments that make dyes vivid. Put together, these ideas turn a flat formula into a 3-dimensional character. Electrons repelling to set the stage, lone pairs nudging the angles, common geometries emerging from simple counts, polarity arising from both bonds and layout, hybrid orbitals explaining identical bond sets, delocalized pi systems, smoothing out bond lengths into symmetrical, unusually stable frameworks. Once you start seeing molecules and shapes rather than strings of letters, their behaviors, Boiling points, solubilities, colors, and reactions begin to feel inevitable. Let that three-dimensional world bloom quietly in your mind. Molecules turning, bending, locking into place, each shape a consequence of electrons seeking space, a geometry written by repulsion and balance. Close your eyes if you haven't already. The chemistry continues whether you're watching or not, patient and eternal. Intermolecular forces, the gentle tugs between molecules. Even the calmest molecules tug on each other, gently, persistently. The faintest pull is London dispersion, tiny momentary dipoles that pop in and out of existence as electrons slosh within a molecule. One instant, a molecule has a little more electron density on one side, and its neighbor responds in kind. The next instant, the ripple has moved. Every substance has these forces, from noble gases to long-chain hydrocarbons, and they grow stronger as molecules get larger and more polarizable. That's why iodine, with its generous electron cloud, is a solid at room temperature, while the smaller fluorine is a gas. More electrons, softer clouds, stronger flickers, higher boiling points. Layered on top of that are dipole-dipole interactions, attractions between molecules that have permanent separation of charge. Point a polar molecule's partially positive end toward another's partially negative end, and they align like tiny compasses. These alignments are not as fleeting as dispersion. They add an extra stickiness that raises boiling points and melting points compared with similarly sized non-polar molecules. Acetone and propane are close in size, yet acetone boils much higher because its carbon-oxygen bond creates a standing dipole that molecules can line up around. There's a special, stronger case of this polar pull called hydrogen bonding, when hydrogen is covalently attached to nitrogen or fluorine. The bond is extremely polar, leaving hydrogen with a pronounced partial positive charge. That hydrogen can then interact strongly with a lone pair on nitrogen, oxygen, or fluorine in a neighboring molecule. The result is a directional cooperative attraction that's stronger than ordinary dipole-dipole forces, but still weaker than covalent bonds. These links knit molecules together into transient networks. Alcohols cling, amides organize, DNA base pairs zip and unzip with exquisite reliability. Replace a single hydrogen bond donor or acceptor, and the texture of a liquid, its solubility, even its aroma, can change noticeably. When intermolecular forces strengthen, bulk properties respond. Liquids become more viscous because molecules have a harder time sliding past one another. They pour slowly, like honey or glycerol. Surface tension rises, pulling the surface taut enough for small objects or insects to rest on it. Boiling points climb because it takes more energy to separate molecules into a gas. Each property is simply a different outward sign of the same inward story. Stronger attractions demand more effort to overcome. Water is the poster child for hydrogen bonding effects. Each water molecule can form up to 4 hydrogen bonds, 2 through its hydrogens, 2 through the lone pairs on oxygen, creating a constantly rearranging network. That network is why water's boiling point is unusually high for such a small molecule, why its heat capacity is generous, and why ice floats. The open tetrahedral arrangement in ice makes it less dense than the liquid. In day-to-day terms, it's why a coastal climate is tempered by the ocean, and why a cup of tea stays warm longer than an equal mass of air would. Sometimes ions join the dance. Ion-dipole forces come into play when a charged ion meets a polar molecule. The classic scene is salt dissolving in water. Noise and Kellever separate from the crystal and become surrounded by oriented water molecules. Oxygen atoms face sodium, hydrogens face chloride. These hydration shells stabilize the ions in solution, paying back the energy cost of pulling the lattice apart. The stronger the ion-dipole attraction and the more favorable the hydration, the more readily an ionic compound dissolves. This is also why salt solutions conduct electricity. The ions, now mobile and well solvated, can carry charge through the liquid. These forces don't exist in isolation. They stack and compete. A large non-polar molecule may rely almost entirely on dispersion and still be a waxy solid if its electron cloud is broad and floppy. A smaller but strongly polar molecule may boil higher than a larger non-polar one because its dipos lock together. Add a few well-placed hydrogen bond donors and acceptors, and the liquid turns syrupy. Remove them, and it thins. Switch from water to a less polar solvent, and ion dipole stabilization weakens, changing solubility. Once you learn to read these invisible tugs, dispersion for everyone, dipoles for the polar, hydrogen bonds for NH, OH, and FH, and ion dipole for charged guests, the everyday world starts making chemical sense. Why perfumes linger, why oils bead on a raincoat, why a pinch of salt melts ice, and why water, humble and abundant, behaves like nothing else. Let those forces settle in your mind like a soft blanket, molecules holding each other, not with the strength of bonds, but with gentle, persistent touches, enough to keep liquids together, enough to make solids soft or hard, enough to give the world its texture. Solids, networks and seas. Some solids are held together so completely that the word molecule barely applies. In network covalent materials, like diamond and quartz, every atom is bonded directly to its neighbors in a continuous three-dimensional framework. There are no discrete units to drift apart, just an endless lattice of strong covalent bonds. To melt such a structure, you must break a vast number of those bonds all at once, which is why their melting points soar and why diamond is so famously hard. Quartz, built from silicon-oxygen tetrahedra, sharing corners throughout the crystal, owes its durability and clarity to the same principle. When the entire solid is one bonded network, heat and force have a lot of work to do. Metals take a different approach to togetherness. In metallic bonding, positively charged metal ions sit in a regular array, bathed in a sea of delocalized electrons. These mobile electrons are not tethered to any single atom. They drift through the lattice. This explains two classic metallic traits at once. First, conductivity. Push on electrons at one end with a voltage, and they flow easily through the material, carrying charge and heat. Second, malleability. When you hammer a metal, layers of atoms can slide without shattering the crystal, because the electron sea continues to hold the ions together. Instead of like charges snapping into alignment and repelling, the glue reforms on the fly, and the sheet bends rather than breaks. Carbon showcases both extremes in a single element. In diamond, every carbon is spatially hybridized, locked into a tetrahedral network. In graphite, carbon is spatially hybridized, forming flat hexagonal sheets with strong sigma bonds in the plane and a cloud of delocalized pi electrons above and below. Those pi electrons can roam along the layers, giving graphite good electrical conductivity in plane. Between layers, only weak dispersion forces hold the sheets together, so they slide easily. The reason graphite makes a good lubricant and why a pencil leaves a trail of carbon sheets that shear off under light pressure. Same element, new geometry, utterly different properties. When it comes to dissolving, the guiding idea is pleasantly simple, like dissolves like. Polar and ionic substances dissolve best in polar solvents, where dipole-dipole and ion-dipole attractions can replace the interactions they had in the solid. Non-polar solutes prefer non-polar solvents, where dispersion forces do the heavy lifting without being outcompeted by strong solvent-solvent attractions. Drop sodium chloride into water, and the partial negative oxygen atoms face sodium, while the partial positive hydrogens face chloride, stabilizing both ions. Try to dissolve the same salt in hexane, and the ions remain lonely and undisturbed with little incentive to separate. Flip the example for grease. Oils ignore water but mingle happily with hexane or toluene, where their soft electron clouds find compatible company. At the boundary between oil and water, a special class of molecules earns its keep. Surfactants have a split personality, a hydrophobic tail that shuns water, and a hydrophilic head that embraces it. When sprinkled into a mixture, these molecules march to the interface and line up, tails in the oil, heads in the water, like tiny bilingual diplomats. This neat arrangement lowers surface tension, making it easier to form droplets and films. At higher concentrations, surfactants assemble into micelles, little spheres with the oily tails tucked inside, which can trap grease and carry it away in the wash. The result is the everyday magic of soaps and detergents. By rewriting the interfacial chemistry, they turn stubborn stains into cooperative guests. Water can also build more elaborate structures when pressured into unusual company. Clathrate hydrates are crystalline cages made of water molecules linked by hydrogen bonds, forming spacious cavities that can trap gas molecules such as methane or carbon dioxide. The gas molecules don't form ordinary chemical bonds to the water. They're physically enclosed, stabilized by the surrounding cage. In the chilly, high-pressure realms under ocean floors and in permafrost, vast deposits of methane hydrate store enormous amounts of gas in solid form, release the pressure or warm the system, and the cages collapse, freeing the guest molecules. This behavior fascinates energy researchers and climate scientists alike, because clathrates blur the line between ordinary ice and a gas reservoir. All of these examples, the unbroken grids of diamond and quartz, the electron sea of metals, the layered conductivity of graphite, the like dissolves like rule of solutions, the choreography of surfactants at interfaces, and the icy cages of clathrate hydrates are variations on a theme. How attractions beyond a single covalent bond shape the feel of matter, change the way electrons are shared or allowed to roam, and you change hardness, melting point, solubility, slipperiness, and the ability to carry charge. The properties we touch and see are the surface ripples of these quiet microscopic arrangements. Your breath is steady now, slow and even. Feel the weight of your body, held together by these same forces, networks and attractions, gentle tugs and firm holds, all working together to keep you whole. Stoichiometry, the arithmetic of chemistry. Chemistry keeps its promises by balancing the books. A balanced chemical equation conserves atoms and charge. Whatever kinds and numbers of atoms you start with must be the same kinds and numbers you finish with, and total charge must match on both sides. The coefficients in front of formulas are not decoration. They're the molar ratios that tell you how many moles of each substance react together. If the equation reads, NeVeChD plus 3 Asians, 2 NHD, that one, 3,2, is a precise recipe at the mole scale. Change the amounts you use, and those ratios tell you what should happen if everything goes perfectly. To scale a recipe up or down, you need a translator between the lab scale of grams and the counting scale of moles. That translator is molar mass. Moles equal sign mass, molar mass. If a sample of carbon dioxide weighs 44 g and its molar mass is 44 g per mole, then you have 1 mole. If you have 22 g, you have 1/2 mole. This simple division unlocks stoichiometry problems, convert all masses to moles, use the coefficients to relate reactants and products, then convert back to grams if needed. In real mixtures, one ingredient usually runs out first. That's the limiting reagent, the reactant that is completely consumed and therefore sets the maximum amount of product that can form. You find it by converting each reactant to the moles of product it could make. The smallest answer wins, and that reactant limits the outcome. The other reactants are present in excess and will be left over once the limiting reagent is gone. Because the world is not perfectly tidy, what you actually collect is often less than what the calculation predicts. Percent yield is a clear scorecard. Percent yield equal sign. Actual yield have theoretical yield. If a reaction should produce 10g of product, but you isolate 8g, the percent yield is 80%. Losses can come from side reactions, incomplete conversion, or a little product left behind on the glassware. Useful reminders that doing chemistry is as much technique as arithmetic. Excess reagent is simply the portion of a non-limiting reactant that remains after the limiting reagent has been used up. Once you know the limiting reagent, you can compute how much of the other reactants were actually required by the molar ratios. Subtract that from what you added at the start, and the remainder is the excess. This is handy for planning. If a reagent is expensive, you don't want to toss most of it down the drain. At the heart of all this counting lies a very large number with a friendly purpose. Avogadro's number is approximately 6.022 cos per mole. It tells you how many atoms, molecules, or ions are in 1 mole of anything. That number is enormous because atoms are tiny, but its job is simple. It lets chemists count unimaginably small particles using everyday amounts of material. Combine conserved atoms and charge, molar masses, limiting reagents, percent yields, and Avogadro's number, and you have the quiet arithmetic that turns a balanced equation into a reliable prediction of what and how much will appear in the beaker. An empirical formula is the simplest way to tell a chemical story. It gives the smallest whole number ratio of atoms in a compound. Glucose, for example, has the molecular formula C-F-O, its empirical formula reduces to C-F-O, the simplest ratio of 1:1. The molecular formula, by contrast, tells you the actual head count. To move from empirical to molecular, you compare the empirical formula mass with the compound's molar mass. If the molar mass is, say, 3 times the empirical mass, then the molecular formula contains 3 empirical units. One elegant path to an empirical formula is combustion analysis. Burn a pure organic sample in excess oxygen and capture the products. All the carbon becomes CO, all the hydrogen becomes HO. Measure the masses of CO and HO produced. Convert those to moles of carbon and hydrogen, and if oxygen is in the original sample, deduce its amount by difference from the total mass. Those mole amounts reduce to a whole number ratio, and that ratio is your empirical formula. It's chemical forensics with fire and a scale. Gases add a useful shortcut. At standard conditions, 0 degrees Celsius and 1 atm, 1 mole of an ideal gas occupies about 22.4. This molar volume lets you count moles from a volume directly when conditions match. If conditions differ, the ideal gas law steps in, PV equals sign nRT. Either way, once you have moles, the balanced equation does the rest. Titration stoichiometry is a quiet duel between measured volumes. A titrant of known concentration reacts with an analyte of unknown concentration according to a balanced equation. At the equivalence point, the mole ratio in the flask matches the stoichiometric ratio on paper. The key arithmetic is straightforward. Moles of titrant added equal sign concentration of titrant quater, volume of titrant. Use the reaction coefficients to find moles of analyte, then divide by the analyte's volume to get its concentration. Indicators or instruments tell you when the stoichiometric balance has been reached. The math tells you how much was in the sample. Gravimetric analysis trusts the scale above all. You convert the analyte into a pure, insoluble compound, filter, wash, dry to constant mass, and weigh. From that mass and the compound's known composition, you calculate how much analyte was present. For instance, precipitating chloride as silver chloride gives you a solid with a fixed ratio of silver to chloride. Weigh the precipitate, convert to moles of alkyl, and the moles of chloride follow 1:1. It's a beautifully direct method. Fewer assumptions, more mass, and the answer appears on the balance readout. Beyond getting the right answer, stoichiometry can help judge how green a synthesis is. Atom economy asks how much of the reactant's mass ends up in the desired product, rather than in byproducts. Atom economy equals sign, mass of desired product, of total mass of reactants. A reaction that rearranges atoms without discarding large fragments scores high. One that lops off bulky, leaving groups, scores low. High atom economy doesn't guarantee a perfect process. Yield, energy use, and safety still matter, but it points the way towards synthesis that wastes less and uses atoms wisely. Let these numbers settle gently. Stoichiometry is not cold arithmetic. It's the language chemistry uses to keep promises, to predict what will form, and to honor the atoms that never vanish, only rearrange. Your mind is drifting now. That's good. Let the moles and ratios blur softly at the edges. Chemistry will still be here when you wake. Gases. The great simplifiers. Gases are the great simplifiers of chemistry, and their favorite rule is the ideal gas law. PV equals sign nRT. Spoken plainly, pressure multiplied by volume equals the number of moles multiplied by the gas constant multiplied by absolute temperature. Hold any two of those steady, and the other pair must adjust. Warm a sealed balloon, and the pressure rises. Let a piston expand while temperature holds steady, and the pressure falls. It's a compact compass for how gases respond when you squeeze them, heat them, add more, or let them spread out. Mixtures of gases behave like polite roommates. Each one presses as if the others weren't there. That's Dalton's law of partial pressures. The total pressure equals the sum of each gas's part. If oxygen contributes 1/3 atm and nitrogen contributes 2/3 atm, the mixture sits at exactly 1 atm. This additivity is why collecting a gas over water requires subtracting the water vapor's partial pressure, and why breathing air at altitude feels different. The total pressure drops, so the partial pressure of oxygen drops with it. Speed in the gas world depends on lightness. Graham's law says effusion and diffusion rates are inversely proportional to the square root of molar mass. In other words, a light gas like helium slips through a tiny pinhole or spreads across a room faster than a heavy gas like xenon. If one gas is 4 times as massive as another, it effuses at half the rate because the square root of 4 is 2. This simple square root relationship explains everything from why helium escapes balloons so quickly to how mass spectrometers can separate gases by their pace. Of course, real gases are not perfectly ideal. Molecules take up space and attract one another a little, and those two facts matter most at high pressures and low temperatures. When molecules have finite size, they can't be squeezed into zero volume. When they attract, they don't hit the container walls as hard as a purely ideal model assumes. The result is deviation, pressures lower than expected, near condensation, volumes larger than expected when particles are bulky, and curves that bend away from the tidy predictions of the ideal equation. To mend the model, the van der Waals equation adds 2 gentle corrections. It replaces V with V wo B accounts for the finite size of molecules, the space unavailable because particles themselves occupy it. It also replaces P with P plus Guézeri, where it accounts for intermolecular attractions that reduce the observed pressure. In words, adjust the volume downward for particle size. Adjust the pressure upward to compensate for attractions that were stealing some push from the walls. Different gases have different A and B values because their sizes and stickiness differ. With those tweaks, predictions about real gases near liquefaction or at high compression become far more faithful. A neat way to measure how real a gas is behaving at a given moment is the compressibility factor, written as Z and defined as Z equals sign PV nRT. For an ideal gas, Z equals sign 1 exactly. If Z1, attractions are winning a bit, and the gas is easier to compress than ideal. If Z1, repulsions or crowding dominate, and the gas is harder to compress than ideal. Plot Sen against pressure, and you get a fingerprint for each gas, a quick visual of how size and stickiness tug the behavior away from perfection. Put these ideas together, and gas behavior becomes predictable without losing its charm. PV equals sign nRT for the broad strokes. Partial pressures add neatly in mixtures. Light molecules outrun heavy ones by a square root edge. Finite sizes and gentle attractions bend the rules. Van der Waals parameters A and B nudge the math back to reality. The compressibility factor Z keeps score on how close you are to the ideal. All of it is the same story told from different angles. Countless tiny particles moving fast, colliding, often, and despite their chaos, obeying a handful of beautifully simple relationships. Breathe in slowly. Hold it. Breathe out. The air you just inhaled, mostly nitrogen and oxygen, follows these very laws, expanding in your lungs, exerting pressure, each molecule jostling independently yet cooperatively. Liquids and solids, viscosity, vapor, and phase. Viscosity is how stubborn a liquid is when asked to move. Honey flows slowly because its molecules cling to one another with strong intermolecular forces and often tangle due to long chains. Water glides more easily because its hydrogen bonds, though numerous, are constantly breaking and reforming, allowing molecules to slip past one another. Raise the temperature, and viscosity usually falls. Heat jostles molecules harder, loosening their grip and making the liquid less resistant to motion. Add stronger attractions, more hydrogen bonding, more polarity, longer chains, and viscosity rises, turning a pour into a leisurely stroll. Every liquid also shares space with its own invisible vapor, and the push from that vapor has a name: vapor pressure. In a closed container, molecules at the surface occasionally escape into the gas phase, while gas molecules return to the liquid. At equilibrium, those rates match. Stronger intermolecular forces hold molecules down more firmly, so fewer escape and the vapor pressure drops. That's why a pan of ethanol evaporates more quickly than an equal pan of water. Ethanol's weaker hydrogen bonding lets more molecules leap into the air, building a higher vapor pressure at the same temperature. Boiling is simply the moment a liquid's vapor pressure equals the external pressure. At that point, bubbles of vapor can form not just at the surface but throughout the liquid, because the vapor inside the bubbles is no longer crushed by the surrounding pressure. Lower the external pressure by climbing a mountain or using a vacuum, and the boiling point falls. Water boils at lower temperatures at high altitude, which is why recipes sometimes need longer cooking times on mountain tops. Increase the pressure, as in a pressure cooker, and the boiling point rises, trapping heat in the pot and cooking food faster. It all hinges on that equality, vapor pressure meeting the pressure outside. Solids come in two broad flavors. Crystalline solids have atoms, ions, or molecules arranged in repeating, orderly patterns that extend in all directions. Salt crystals, quartz and metals fit this description. Their repeating lattices explain sharp melting points, and often well-defined faces and cleavage planes. Amorphous solids, by contrast, lack long-range order. Glass and many plastics are frozen into place without settling into a repeating pattern. They soften over a range of temperatures rather than melting sharply, and their properties can vary subtly with how they were cooled and processed. Order or no order. The different shapes how solids fracture, conduct heat, and interact with light. Some elements can wear different structural outfits called allotropes, and carbon is the celebrity example. Arrange carbon atoms into a rigid three-dimensional network with each atom bonded to 4 neighbors, and you have diamond, extremely hard, optically brilliant, and an outstanding conductor of heat but not electricity. Arrange them in flat hexagonal sheets with each atom bonded to 3 neighbors, and you have graphite, soft, slippery, and electrically conductive along the planes, thanks to delocalized pi electrons. Same element, same atoms, entirely different properties because bonding and geometry change. Allotropy appears elsewhere too. Oxygen can be diatomic, orthose, or triatomic ozonoform. But carbon's contrast between diamond and graphite is a vivid reminder that structure dictates behavior. Not every solid needs a liquid phase to escape into a gas. Sublimation is the direct transition from solid to gas without a liquid middle step. Dry ice, solid carbon dioxide, is famous for this. At ordinary atmospheric pressure, it doesn't melt, it simply turns into CO2 gas, rolling off as a cold fog. Naphthalene in mothballs and iodine crystals will also slowly sublime at room temperature, releasing a telltale smell or violet vapor. Whether a substance sublimates easily depends on the shape of its phase diagram. If the triple point, where solid, liquid, and gas coexist, sits above everyday pressures, the material can skip the liquid state entirely under normal conditions. Put these pieces together, and the behavior of liquids and solids becomes intuitive. Stronger attractions knit liquids into more viscous, higher boiling, lower vapor pressure states. External pressure sets the bar for boiling by deciding when bubbles can stand their ground. Order versus disorder in solids separate sharp melting crystals from softening glasses. Allotropes remind us that the same atoms arranged differently make new worlds of properties. And sublimation shows that phase changes are about energy and pressure, not a compulsory march from solid to liquid to gas. When you watch a raindrop bead on a waxed leaf, see a kettle boil sooner at sea level than on a mountain, or feel the slick trace of graphite from a pencil, you're seeing these quiet principles in motion. Let your thoughts drift like vapor rising from warm water, slow, weightless, inevitable, chemistry unfolding in every direction, whether you're awake to see it or not. As daylight softens and the world grows quieter, let's take a gentle journey into the heart of matter itself, where atoms dance in patterns as old as time, and chemistry unfolds like a lullaby written in elements. The silent symphony of molecules. Somewhere in the quiet dark of a molecule, sound vanishes into silence, yet even in that stillness, chemistry hums with life. Racemates crystallize differently from their pure enantiomers, like mirror twins who prefer different rooms. Chiral environments, the curved spaces inside enzymes, gently separate these molecular siblings, favoring one hand over the other with the patience of water shaping stone. Not all stereochemical siblings are perfect mirrors. Diastereomers are cousins rather than twins, stereoisomers that aren't reflections of each other. Unlike enantiomers, they carry different melting points, boiling points, densities. Even the way they dissolve feels distinct. Two sugars with identical formulas can be diastereomers and taste wonderfully different, one sweet as honey, another barely sweet at all. Two drug candidates can be diastereomers, where one crystallizes neatly into sparkling order while the other stubbornly oils out, refusing the crystal's call. Because their physical natures differ so clearly, Diastereomers are often easier to coax apart than enantiomers, a practical gift that synthetic chemists treasure, like finding the right key on the first try. The geometry of double bonds. Double bonds bring their own quiet geometry, labeled with easy notation like compass directions on a molecular map. To assign it, give each carbon of the double bond a priority for its two substituents using the Kahn-Ingold-Prelog rules. Higher atomic number means higher priority, and if there's a tie, look outward along the chain like following a trail through the woods. If the higher priority groups rest on the same side of the double bond, the alkene is Z, from the German zusammen, meaning together. If they sit on opposite sides, it's E, from entgegen, meaning opposite. This system works even when cis and trans would be ambiguous, and it maps directly onto properties like boiling point and reactivity that depend on shape. The way a molecule folds determines how it moves through the world. At a single chiral center, absolute configuration is captured by RS notation. Rank the four substituents by the same priority rules, then orient the molecule so the lowest priority group points away from you, like turning a puzzle piece to catch the light. Trace a path from highest to second to third priority. If the path turns clockwise, the configuration is R from the Latin rectus, meaning right. If it turns counterclockwise, it's S, from sinister, meaning left. R and S don't tell which way plane polarized light rotates. That must be measured. A little secret kept until experimentation reveals it. But they do give an unambiguous structural label that any chemist anywhere can reproduce from a drawing, a shared language written in priorities and handedness. Handedness in living systems. Living systems are exquisitely picky about handedness. Enzymes, receptors, and transporters are themselves chiral, built with preference woven into their folds, so they often recognize one enantiomer far better than the other, like a lock that accepts only one specific key. One enantiomer of limon smells like fresh oranges. Its mirror image smells like pine forests after rain. One enantiomer of a medicine may bind tightly and offer healing, while the other may be weaker, inactive, or even cause unwanted side effects. That's why modern drug synthesis and analysis are obsessed with stereocontrol and chiral purity, because in biology, a mirror image can tell an entirely different story. Polymers. Long stories told in repeating words. Polymers are long stories told in repeating words, and the way those words link changes everything. In addition, polymerization, monomers with double bonds open those pi bonds like doors swinging wide and join hands end to end. No small molecules leave. The chain simply grows as each new double bond adds to the reactive end, link by link, in a patient march. Vinyl chloride turns into polyvinyl chloride, ethene becomes polyethylene, styrene becomes polystyrene. Often a radical, cation, or anion starts the chain, and once it's moving, the process cascades like a gentle avalanche. Initiation creates the first reactive site, propagation adds monomer after monomer in a rapid but orderly march, and termination finally caps the chain, sealing it like the last stitch in a seam. The key point is the bookkeeping. The atoms present at the start end up in the backbone. Nothing is lost, only rearranged. Condensation polymerization writes a different kind of sentence, punctuated by the release of tiny byproducts. Two complementary functional groups react to form a bond while eliminating a small molecule such as water or methanol. A tiny farewell with each new link. Diols with diacids form polyesters. Diamines with diacids form polyamides like nylon, those smooth, strong fibers that changed how the world dresses. Bisphenol, A with epichlorohydrin yields epoxy networks, rigid and resilient. Each new link comes with a whisper of departure, a drop of water here, a whiff of methanol there, and the chain lengthens as those small molecules float away. Because functionality matters, monomer design is like engineering a zipper, matching teeth on both sides to get a strong, even closure. Thermoplastics and thermosets. Heat treats polymers according to how they're built. Thermoplastics are like wax. They soften when warmed and can be reshaped because their chains are not permanently tied together. Melt and mold, cool and harden, repeat as needed, in cycles as gentle as breathing. Thermosets are different. Once cured, they form cross-linked networks where chains are tied together at many points, creating a web that cannot flow when heated. Instead, it chars or decomposes, holding its shape to the very end. Epoxies, vulcanized rubber, and many resins are thermosets, chosen when rigidity, heat resistance, or chemical resilience matters more than recyclability. A polymer's personality depends on chain length, branching, and crystallinity. Longer chains tangle more, raising viscosity and strength like threads woven tighter. Branching changes how neatly chains can pack. High-density polyethylene has very little branching and packs tightly into crystalline regions, making it tough and stiff. Low-density polyethylene has many branches that frustrate packing, yielding a softer, more flexible material, pliable and forgiving. Crystallinity creates ordered lamellae that raise melting points and improve barrier properties. Amorphous sections lend clarity and impact resistance, a balance between order and flexibility. Even the glass transition temperature, the point where an amorphous polymer shifts from glassy and brittle to rubbery and flexible, is tuned by how tightly chains interact and how freely they can wiggle, like dancers finding room to move. Copolymers, mixing monomers to tune behavior. Mixing monomers is a powerful way to tune behavior, and copolymers are the result. Random copolymers sprinkle two monomer types along the chain, smoothing properties between the parents like blending two colors on a palette. Block copolymers stitch long runs of one monomer to long runs of another, and those blocks can self-assemble into nanoscale domains that grant rubbery toughness and clear phase morphologies. Think styrene butadiene styrene in shoe soles, hard and soft layers interleaved in quiet cooperation. Graft copolymers hang side chains of one polymer on the backbone of another, creating emulsifiers or impact-modified plastics like ABS, where styrene acrylonitrile backbones carry rubbery butadiene grafts for crack resistance. By changing composition and sequence, engineers dial in flexibility, transparency, gas barrier performance, and processability, sculpting materials to meet the moment. Biodegradable polymers. Not every plastic is here to stay. Biodegradable polymers are designed to come apart under the right conditions, breaking their chains by hydrolysis or with help from enzymes. Polylactic acid hydrolyzes its ester links and composts under industrial conditions. Polycaprolactone and polyglycolic acid do the same more slowly, which is useful in medical sutures and drug delivery devices that should vanish after their job is done, leaving no trace. Polyhydroxyl-cannanotes are brewed by microbes and can be digested by microbes again, closing a biological loop as elegant as seasons turning. Biodegradable doesn't mean disappears overnight. Temperature, moisture, microbes, and oxygen all matter, but with the correct environment, these materials return to simpler molecules rather than lingering for decades, gracefully stepping off stage when their performance is over. From addition chains that keep every atom to condensation steps that leave tiny footprints, from meltable thermoplastics to permanently cross-linked thermosets, from backbone length and branching that set strength and flexibility to copolymer architectures that blend virtues, and finally to polymers that gracefully dissolve back into the earth. Macromolecules are a chemistry of design where small structural choices ripple into the textures, strengths, and lifetimes of the things we touch every day. Proteins, elegant chains, built from a standard toolkit. Proteins are long, elegant chains built from a standard toolkit of 20 amino acids. Each amino acid has an amino group and a carboxyl group, and when two meet, they link by forming a peptide bond, a condensation reaction where the carboxyl of one and the amino of the next combine and release water, like hands clasping with a gentle exhale. Stack that reaction thousands of times, and a polypeptide emerges, a backbone of repeating NCC units with side chains, or groups, jutting out like charms on a bracelet. Those side chains, acidic, basic, polar, nonpolar, bulky, or tiny, are the characters that give each protein its personality. The primary structure of a protein is the exact order of those amino acids, letter by letter, like a sentence written in a 20-letter alphabet. From that one-dimensional script springs higher-order structure. The chain folds into local motifs, alpha helices and beta sheets, then packs into a three-dimensional shape that places catalytic residues, binding pockets, and flexible hinges exactly where they're needed. Finally, multiple folded chains may assemble into a larger complex. Sequence begets shape, shape begets function. Change a single letter in the primary structure, and the meaning of the entire sentence can shift, like a word misheard in the dark. Forces that hold proteins together. What holds a folded protein together is a tapestry of small forces working in chorus. Hydrogen bonds stitch alpha helices and beta sheets into place, lining up backbone carbonyls and NH groups with zipper-like regularity. Hydrophobic side chains flee water and huddle together in the interior, driving the overall collapse of the chain. The hydrophobic effect is the backstage crew that dims the house lights and gets the actors on stage. Ionic interactions, salt bridges, bring oppositely charged side chains into snug pairs, adding strength and tuning stability with pH. Disulfide bonds, covalent links between cysteine residues, act as molecular safety pins, locking distant parts of a protein together and hardening extracellular proteins against the rough-and-tumble world outside the cell. Enzymes, making chemistry fast. Enzymes are proteins, and sometimes RNAs that make chemistry fast by making the hills smaller. They lower the activation energy of a reaction, increasing the rate, but they don't change the overall equilibrium. Reactants and products still balance as thermodynamics dictates. Think of an enzyme as a trail crew carving switchbacks up a steep mountain. The summit is the same, but the path is easier and faster to climb. That's why tiny amounts of enzyme can process vast amounts of substrate in short order, again and again tirelessly. The magic happens in the active site, a pocket or groove where the substrate binds with high specificity. Specificity isn't a single handshake. It's a constellation of weak interactions, hydrogen bonds, van der Waals contacts, hydrophobic packing, and precisely placed charges. Some enzymes use induced fit, flexing subtly when the substrate arrives to align catalytic residues exactly and to stabilize the transition state. Others pre-organize a charged environment so that the toughest step in the reaction is prepaid by complementary electrostatics. Either way, the active site is a carefully arranged microenvironment, more like a custom toolkit than a simple slot. Denaturation. Despite their robustness, proteins are sensitive to their surroundings, and denaturation shows just how much their function depends on shape, heat, extreme pH, high salt, organic solvents, or heavy metals can disrupt the non-covalent interactions that hold the folded structure together. The protein unravels, losing secondary, tertiary, and quaternary structure, and function vanishes like a song played backwards. Crucially, the peptide bonds of the backbone usually remain intact during denaturation. The chain is still there, but the three-dimensional architecture is gone. That's the difference between an egg's clear protein turning opaque in a frying pan, denaturation, and chopping the protein into amino acids, hydrolysis. In the right conditions, some proteins can refold and regain activity. Others need chaperone proteins to guide the process. Still others are past the point of no return. Put these pieces together, and proteins become less mysterious and more inevitable. A linear sequence written by genes folds by local rules into stable motifs, packs by hydrophobic collapse, and precise side chain interactions into a functional machine, binds substrates in an active site tailored by evolution, accelerates reactions by easing the hardest step, and unravels when the environmental threads that hold it together are pulled. From silk's strength to hemoglobin's oxygen shuttle to enzymes that stitch and snip DNA, the same principles of bonding, folding, and specificity echo across biology's molecular stage. Carbohydrates, quick change artists. Carbohydrates are nature's quick change artists, switching from sweet, simple sugars to sturdy structural beams with just a change in linkage. Glucose can polymerize into starch for energy storage in plants, using alpha-1, 4 links with occasional alpha-1, 6 branches in amylopectin, branches that our enzymes can snip for fuel, like cutting kindling for a fire. Arrange the very same glucose in beta-1, 4 links, and you get cellulose, long, straight chains that hydrogen bond into tough fibers, perfect for plant cell walls, and impossible for our digestive enzymes to untangle. Animals echo starch's logic with glycogen, a highly branched glucose store ready for rapid release. Same monomer, different joinery, wildly different jobs. Lipids, assembling membranes. Lipids assemble membranes by using their split personalities. Each phospholipid has a hydrophilic head that loves water and a pair of hydrophobic tails that avoid it. In water, they spontaneously form bilayers, heads out, tails in, a self-sealing sheet that becomes the cell membrane. Proteins float and drift within this fluid mosaic, carrying signals, pumping ions, and ferrying nutrients. Cholesterol slips between tails to keep the membrane from getting too floppy when it's warm and too brittle when it's cold, like a gentle hand adjusting the thermostat. Under other conditions, lipids can roll into micelles or curve into vesicles, little bubbles that cells use to ship cargo or capture meals. Nucleic acids, life's libraries. Nucleic acids are life's libraries. DNA stores genetic information in 2 antiparallel strands coiled into a right-handed double helix, graceful as a spiral staircase. The code is written with 4 bases that pair with exquisite specificity. Adenine pairs with thymine through 2 hydrogen bonds, and cytosine pairs with guanine through 3. Because each strand is a template for its partner, the molecule can be copied with high fidelity, unzip, match the bases, and rewind, simple as opening and closing a book. RNA reads from this library and acts messenger. RNA carries instructions. Transfer RNA delivers amino acids. Ribosomal RNA helps build proteins, and many small RNAs fine-tune expression like editors with sharp pencils. ATP, the cell's rechargeable coin. ATP is the cell's rechargeable coin, paying for uphill chemistry. Its high-energy phosphate bonds aren't spring-stuffed with magic. The hydrolysis simply shifts the balance to more stable, better solvated products. In words, adenosine triphosphate plus water yields adenosine diphosphate plus inorganic phosphate and a proton, releasing usable free energy under cellular conditions. Enzymes couple this release to hard tasks, shaping proteins, pumping ions, building polymers, often by forming a brief phosphorylated intermediate. Magnesium ions steady the triphosphate's negative charges, and kinases act as cashiers, moving the phosphate group exactly where it's needed. Cofactors and coenzymes. Enzymes rarely work alone. Many carry small helpers that do the tricky electron or group transfers. Metal-ion cofactors, like zinc adenines and iron polarize bonds or shuttle electrons. Organic coenzymes, often derived from vitamins, do precision courier work. Nedaline and FAD carry hydride or hydrogen atom equivalents in redox reactions. Coenzyme A delivers activated 2-carbon units as thyristors. Pyridoxal phosphate moves amino groups in transamination. Biotin carries carbon dioxide in carboxylations. By swapping these portable parts, a single protein scaffold can handle a wide repertoire of chemistry, versatile as a Swiss Army knife. Metabolism, choreography, not chaos. Metabolism is choreography, not chaos. Pathways are sequences of enzyme-catalyzed steps that pass intermediates hand to hand with regulation built in so supply meets demand. Feedback inhibition is a favorite trick. Make enough of the end product, and it circles back to slow the first committed step, preventing waste like turning down the tap when the bucket is full. Allosteric enzymes read the room, activators or inhibitors bind at regulatory sites, and shift the protein shape to speed or slow the flow. Catabolic routes harvest energy by breaking molecules down. Anabolic routes spend that energy to build. Compartmentalization adds another layer. Fatty acid oxidation in mitochondria. Fatty acid synthesis in the cytosol. Same actors, different stages, directions never crossed. Alloys. The chef's specials of the metal world. Alloys are the chef's specials of the metal world. Take a base metal, blend in carefully chosen partners, and tune strength, toughness, conductivity, and corrosion resistance like adjusting spices in a recipe. Steel is iron seasoned with carbon and often chromium, nickel, or molybdenum. Brass is copper, mixed with zinc for a golden sheen and easy machinability. Bronze brings copper together with tin for wear resistance. By altering composition and processing, the same family of atoms can become a spring, a scalpel, or a skyscraper. Heat treatment, artistry that follows the recipe. Heat treatment is the artistry that follows the recipe. Heat a steel to austenite, quench it fast, and trap a hard supersaturated phase called martensite. Temper it, reheat gently, and trade a bit of hardness for crucial toughness. Annealing softens and relieves internal stresses. Normalizing refines grain size for uniform properties. All of these processes rearrange the microstructure, the sizes and shapes of grains and the phases present, and that invisible landscape determines how the metal bends, dents, or cracks when real forces arrive. Stainless steels, self-healing armor. Stainless steels wear self-healing armor. With enough chromium, typically at least about 12%, the surface oxidizes to a thin, tightly adherent chromium oxide layer that shuts down further corrosion. Scratch it, and in the presence of oxygen, the film reforms on its own, quietly mending. Add nickel for austenitic grades that are easy to form and weld. Add molybdenum to boost pitting resistance in chlorides. The bulk metal provides strength. The nanometer-thin passive film provides durability, a partnership that keeps cutlery bright and chemical plants safe. Shape memory alloys, remembering their youth. Some alloys remember their youth. Shape memory alloys. The celebrity is nickel titanium, often called nitinol, undergo a reversible solid-state phase change between martensite and austenite. Deform them in the low-temperature martensitic state, and the distortion twirls through the crystal like reversible origami. Warm them past a transition temperature, and the lattice snaps back to the austenitic form, carrying the macroscopic shape with it. That heat to reset trick powers self-expanding stents, actuators, and eyeglass frames that shrug off bends with quiet dignity. Superconductors, materials without resistance. In the quiet below a critical temperature, certain materials lose all electrical resistance. They become superconductors. Push a current, and it flows without dissipation, like water flowing endlessly in a closed loop. Bring a magnet close and the Meissner effect expels the magnetic field, letting the superconductor levitate a magnet like a magic trick with Maxwell's blessing. Traditional low-temperature superconductors need cryogenic baths. Newer high-temperature ceramics operate in liquid nitrogen ranges, still chilly, but far more practical. The promise is cables with zero loss, ultra-sensitive magnets for imaging and accelerators, and perhaps one day, more accessible power technologies. Interstitial strengthening. A tiny atom in a tight spot can make a big difference. Interstitial strengthening occurs when small atoms, carbon, nitrogen, or hydrogen, squeeze into the gaps of a metal lattice, as carbon does in iron. Those interstitials distort the crystal and snag dislocations, the line defects that enable metals to deform. With dislocations pinned, more stress is required to make the lattice slip, so hardness and yield strength rise. This is the essence of steel. A little carbon threaded between iron atoms turns a soft, easily dented metal into a workhorse that holds an edge, bears a load, and builds a city. Ceramics. The Stoics of materials. Ceramics are the Stoics of materials, hard, heat-resistant and unflappable under compression, yet prone to sudden failure when stretched or struck. Their atoms are locked together by strong ionic and covalent bonds. Think of aluminum oxide, silicon carbide, or zirconium dioxide, which give them high melting points and superb wear resistance. But those same bonds restrict dislocation motion, the microscopic slipping that lets metals bend, so cracks in ceramics have little way to blunt or heal. Flaws matter. A tiny surface scratch can focus stress and launch a fracture. Engineers counter this with clever microstructures, adding zirconia to transformation-toughen alumina or designing compressive surface layers. But the fundamental trade-off remains great stiffness and heat tolerance, bought at the price of brittleness. Glass, a solid that never learned the crystal's choreography. Glass is a solid that never quite learned the crystal's choreography. It's amorphous. Atoms are arranged like a frozen liquid, without long-range order. Pure silica glass melts at punishing temperatures, so modifiers are added to tune behavior. Sodium oxide lowers the melting point. Calcium oxide restores chemical durability. Together, they make everyday soda-lime glass for windows and bottles. Add boron oxide, and you get borosilicate glass, which resists thermal shock in labware and cookware. Titania, alumina, and rare earth oxides tweak refractive index and dispersion for optics and fiber communications. By adjusting the network formers and modifiers, glassmakers dial transparency, hardness, thermal expansion, and even how a glass breaks, engineering fragility with precision. Semiconductors. Between insulators and metals. Semiconductors sit between insulators and metals, and a sprinkle of the right impurity gives them purpose. Doping with donor atoms like phosphorus in silicon creates N-type material with extra electrons ready to conduct. Doping with acceptor atoms like boron in silicon creates P-type material with mobile holes, missing electrons that move as positive charges. Join N-type and P-type, and you form a p-n junction, the one-way gate at the heart of diodes, transistors, and solar cells. Bias the junction and carriers flow, reverse it, and the current nearly stops. With nothing more than a few parts per million of dopants, conductivity can shift by many orders of magnitude, the subtlety that underpins modern electronics. Light-emitting diodes. Light-emitting diodes turn electricity straight into light by letting electrons and holes reunite in a semiconductor. When an electron from the conduction band falls into a hole in the valence band, it can release the energy difference as a photon. The color is set by the band gap. Wider gaps give bluer light, narrow gaps give redder light. Efficient LEDs engineer PN junctions, confining layers and reflective structures so that most recombinations produce photons and most photons escape. The result is a cool-running, long-lived light source that wastes little energy as heat. Indicator dots, phone screens, street lamps, and plant grow panels all sing from this same quantum chorus. Perovskites, a family with shared blueprint. Perovskites are a family of materials with a shared blueprint, the ABXC structure, but a dazzling range of personalities. Swap the A site and large cation, the B site, a smaller cation, or the X site, an anion, often oxygen in oxides or halides in solar absorbers, and you tune band gaps, dielectric constants, and magnetic or ferroelectric behavior. Calcium titanate is the namesake. Barium titanate is ferroelectric. Halide perovskites with lead or tin absorb sunlight strongly and can be tuned from deep red to sky blue by adjusting the halide mix. That structural flexibility lets researchers dial in electronic and optical properties for sensors, photovoltaics, lasers, and light emitters, a single lattice hosting many technologies. Conducting polymers. Some plastics behave like wires in disguise. Conducting polymers carry charge along conjugated peer systems, chains of alternating single and double bonds where electrons are delocalized. Polyaniline, polypyrrole, and polythiophene derivatives like p-DOTE, PSS can be doped to create mobile charge carriers called polarons and bipolarons, turning a dull organic film into a flexible, transparent electrode or a soft biointerface. Because they can be printed as inks, stretched, or interfaced with living tissue, conducting polymers bridge electronics and biology, making bendable circuits, smart textiles, and electrodes that can talk to cells in their own gentle, watery language. Ozone, a thin shield above our heads. High above our heads, a thin shield of ozone soaks up the sun's most harmful ultraviolet rays. Ozone is just oxygen in a different arrangement. 3 atoms instead of 2, but that extra atom makes it uniquely good at absorbing high-energy light before it reaches skin, eyes, and DNA. For decades, chlorofluorocarbons drifted upward from sprays and coolants, and under sunlight, split to release chlorine radicals. Those radicals enter catalytic cycles where one chlorine atom can destroy many ozone molecules before being parked temporarily as reservoir species, only to be reawakened by sunlight and keep going. The result was the infamous springtime hole over Antarctica. Not a literal hole, but a dramatic thinning. International agreements phasing out these chemicals have helped the layer recover, a rare win where chemistry diagnosed a planetary problem and chemistry policy helped solve it. Photochemical smog. Hazy city afternoons have their own chemistry lab in the sky. Photochemical smog forms when nitrogen oxides from engines and power plants meet volatile organic compounds from fuels, solvents, and even trees. Then sunlight flips the switch, and a cascade of reactions produces ozone at ground level. Great up high, irritating down low, along with a medley of oxidants and secondary organic aerosols. Temperature inversions trap the brew, and the familiar brownish haze builds. Because sunlight drives the chemistry, smog tends to peak on calm, warm days, and the recipe can be tuned by local emissions. Cut nitrogen oxides or volatile organics too unevenly, and the cleanup may not arrive as expected. Smart air quality plans balance both sides of the equation. Acid rain. When rain falls through air laced with sulfur dioxide and nitrogen oxides, the droplets become tiny acid factories. In the atmosphere, sulfur dioxide oxidizes to sulfuric acid and nitrogen oxides become nitric acid. Clouds and fog efficiently dissolve these acids and deliver them to the ground as acid rain. The consequences ripple outward. Lakes lose buffering capacity and become too acidic for fish eggs. Soils leach essential nutrients like calcium, metals corrode faster, limestone carvings soften, flue gas desulfurization, low sulfur fuels, and catalytic converters have slashed many emissions, proving that targeted chemical controls can protect ecosystems without turning off the lights. Greenhouse gases. Some gases act like a comforter around the planet. Greenhouse gases such as carbon dioxide, methane, nitrous oxide, and water vapor absorb infrared radiation that Earth emits after it warms in sunlight, then re-emit that energy in all directions, including back down. This slows the escape of heat, nudging surface temperatures upward. Different gases trap heat with different strengths and lifetimes. Methane packs a stronger short-term punch, but persists for a shorter time than carbon dioxide. Carbon dioxide is gentler per molecule but lingers, accumulating with every ton emitted. Understanding their spectra and life cycles is the chemistry behind climate models, and the reason reducing long-lived emissions is central to stabilizing temperatures. Particulate matter. Not all air pollution is invisible. Particulate matter, tiny solid and liquid particles suspended in air, affects health and climate in ways that depend on size and composition. PM2, particles 10 micrometers and smaller, can irritate the upper airways. PM2, issue 2.5 micrometers and smaller, penetrates deep into lungs and can enter the bloodstream. Soot absorbs sunlight and warms. Sulfate and nitrate aerosols scatter light and cool. Organic aerosols can do both, depending on their mix. Particles also carry metals and organics that trigger inflammation. Chemistry determines how these particles form, direct emissions versus secondary formation, how long they linger, and how best to remove their sources. Atmospheric cycles. Above cities and forests alike, atmospheric chemistry quietly runs the nitrogen and sulfur cycles that set the stage for life. Nitrogen oxides formed in lightning, and engines can become nitric acid and ultimately nitrates that fertilize soils, helpful in moderation, harmful in excess when they overfeed waterways. Sulfur from volcanoes and combustion converts to sulfate aerosols that seed clouds and alter Earth's reflectivity. Microbes close loops at the surface, reducing nitrates back to nitrogen gas or oxidizing reduced sulfur to sulfate, while winds and sunlight keep reagents moving. The sky is not empty. It's a dynamic reactor that shuttles atoms among reservoirs, deciding whether nutrients nourish, metals rust, skies clear or haze forms. Water hardness and softening. When tap water leaves spots on glassware and soap refuses to lather, the culprit is often hardness, mainly calcium aldehydes and magnesium aldehydes, dissolved from limestone and dolomite. These ions grab onto soap to form insoluble scum and compete in detergents with the cleaning desired. One elegant fix is ion exchange. In a softener, a resin loaded with sodium ions or sometimes potassium ions trades places with incoming calcium aldehydes and magnesium aldehydes, capturing the hardness ions and releasing harmless sodium ions into the water. When the resin fills up, a brine rinse resets it, sending the captured calcium and magnesium down the drain and restoring the resin's appetite. Eutrophication. Give a lake too much fertilizer, and it throws a green party with an ugly hangover. Eutrophication happens when nutrient runoff, mostly nitrates and phosphates from agriculture, lawns and wastewater, fuels explosive algal and cyanobacterial blooms. At first, photosynthesis may spike oxygen in daylight, but when the bloom dies, microbes feast on the sinking biomass and consume dissolved oxygen in the process. Oxygen drops, fish suffocate, and bottom-dwelling creatures flee or perish. The water turns murky, food webs skew, and toxins from some species can make matters worse. The chemistry cure is prevention. Cut nutrient inputs, restore wetlands that intercept runoff, and time fertilizer so plants, not waterways, get the feast. Heavy metals and chelation therapy. Some elements don't stay politely diluted. They climb the food chain. Heavy metals such as mercury, cadmium, and lead can bioaccumulate in organisms and biomagnify at higher trophic levels. So a top predator can end up with concentrations thousands of times higher than the surrounding water. In medicine, one countermeasure is chelation therapy. Chelators are claw-like molecules. For example, EDTA for lead, dimercaptosuccinic acid for certain arsenic and mercury exposures, that bind metals using multiple donor atoms, wrapping them into water-soluble complexes that the body can excrete. It's a delicate tool. The same legs can also grab essential ions like zinc adhav or calcium colv, so dosing and selection are done with care. Activated carbon. When water carries a whiff of solvent or tastes faintly chemical, activated carbon often comes to the rescue. Made by pyrolyzing and activating carbonaceous materials, it has an immense internal surface area, hundreds to over 1,000 square meters per gram. That vast landscape adsorbs organic molecules through van der Waals forces, and for some pollutant-specific interactions, activated carbon absorbs taste and odor compounds, pesticides, and many industrial organics. Packed into filter beds or granular cartridges, it polishes drinking water and protects fish in aquaria. In wastewater plants, it captures hard-to-biodegrade micropollutants that slip past biology. Soil redox chemistry. Beneath our feet, soils run on redox rules. Where oxygen is plentiful, iron sits mostly as ionocorves in insoluble oxides and hydroxides that lock phosphorus and some trace metals onto particle surfaces. Let the soil become waterlogged and oxygen poor, and microbes turn to alternative electron acceptors, reducing ionocorv to ionocorv, which is more soluble. Arsenic, often adsorbed to ionocorv oxides, can be released under these reducing conditions and leach into groundwater. Manganese shows similar mobility swings between manganese hawat and manganese corv, drain the soil, and oxygen returns. Iron reoxidizes and metals can reattach. Managing water tables and organic inputs is therefore chemistry by way of hydrology. Control the redox and control what moves. Desalination. Turning seawater into drinking water looks simple until the energy bill arrives. Desalination leans on two main strategies. Distillation boils water, condenses the vapor, and leaves salts behind. Reliable but energy-hungry, because the latent heat of vaporization must be supplied, though multiple effect and vapor compression designs recycle heat to trim costs. Reverse osmosis uses high pressure to push water through semi-permeable membranes against the natural osmotic flow, rejecting most salts and many contaminants. Energy recovery devices now recapture pressure from the brine stream, making modern reverse osmosis markedly more efficient than early systems. Both approaches demand careful pre-treatment to prevent fouling and scaling, and both produce a concentrated brine that must be managed responsibly. The chemistry is clean. The engineering challenge is to do it with minimal energy and minimal environmental footprint. From swapping out hardness ions to halting algal avalanches, from catching metals with molecular claws to polishing water on carbon's vast internal landscapes, from soil redox switches that open and close elemental traffic to the energy calculus of turning oceans into taps. Environmental chemistry is a toolkit for keeping water and soil healthy, clear, and alive. UV visible spectroscopy. Shine ultraviolet or visible light through a solution, and some wavelengths will be gulped down by electrons leaping to higher energy states. That's UV visible spectroscopy in a sentence. It measures electronic transitions, and the darker the gulp, the more of the absorbing species present. The Beer-Lambert law makes this quantitative absorbance equals molar absorptivity multiplied by path length multiplied by concentration. In symbols, A equal fan, A equal fan, A, E, E, C. Epsilon is the dye or molecule's inherent ability to absorb at that wavelength. LL is how far the light travels through the sample, often 1 centimeter, and CC is the concentration. Plot absorbance versus concentration for a standard series, and unknown concentrations can be read straight off the line like a ruler made of light. Infrared spectroscopy. If UV-Vis tells how much, infrared spectroscopy whispers what kind. Molecules vibrate, bonds stretch, bend, twist, and each functional group has preferred frequencies, like instruments in an orchestra. An OH stretch near 3,400 wave numbers announces an alcohol. A sharp carbonyl peak near 1,700 wave numbers signals an aldehyde or ketone. The fingerprint region below 1,500 wave numbers is a dense thicket of unique patterns, record which IR wavelengths are absorbed, and a map of functional groups emerges without ever opening the molecule. Nuclear magnetic resonance. Nuclear magnetic resonance, NMR, lets chemists eavesdrop on atoms by listening to their spins in a magnetic field. Hydrogen and carbon nuclei behave like tiny bar magnets. In a strong field, they align and precess at frequencies exquisitely sensitive to their electronic neighborhoods. Shielding by electrons shift signals upfield or downfield, so chemical shift reveals what's nearby: an electronegative atom, a pi system, an alkyl chain. Splitting patterns, doublets, triplets, quartets, arise when neighboring spins couple, counting the number of adjacent hydrogens, like notches on a doorframe. Integration tells how many hydrogens contribute to a signal. Put these clues together, and NMR writes out the molecule's connectivity in a language of peaks and spacings. Mass spectrometry. Mass spectrometry weighs charged fragments with breathtaking precision, ionize molecules by electron impact, electrospray or another method, and accelerate the resulting ions through electric or magnetic fields. Because the path an ion takes depends on its mass-to-charge ratio, Ma/Z, the detector records a spectrum of peaks whose positions and heights reveal both the molecular mass and characteristic fragments. A molecular ion peak hints at the intact mass. A pattern of losses, 18 mass units for water, 15 for a methyl, sketches the functional groups. High-resolution instruments can even distinguish between formulas that differ by a fraction of a Dalton, turning the spectrum into a chemical fingerprint. X-ray diffraction. When there's a crystal, X-ray diffraction is the gold standard for seeing atoms where they live. X-rays reflect and interfere from the periodic planes in a crystal lattice, producing a pattern of spots whose positions and intensities encode the three-dimensional arrangement of atoms. By solving the diffraction pattern, electron density maps are recovered, and atoms placed with angstrom-level accuracy. Bond lengths, bond angles, hydrogen bonds, metal coordination, all revealed. This is how the shapes of complex minerals, pharmaceuticals, metal organic frameworks, and even protein structures, when they can be coaxed to crystallize, are known. Fluorescence. Some molecules do more than absorb light, they glow. In fluorescence, a molecule absorbs a photon and jumps to an excited electronic state, then relaxes a little, losing some energy as heat, before emitting a new photon as it falls back down. Because of that relaxation, the emitted light has a longer wavelength, lower energy than the absorbed light, a Stokes shift that makes fluorescence easy to spot with filters. Sensitive detectors can see even faint glows, so fluorescence underpins everything from DNA dyes in gels to fluorescent proteins in cells. From environmental sensors that blink when they bind a pollutant to barcodes read by scanners, light in, a softer light out, and a wealth of information in the color and brightness of the glow. Chromatography. Chromatography is like sending a crowd through a maze where different people are distracted by different sights along the way. A mixture is carried by a mobile phase past a stationary phase, and each component interacts a little differently with what it passes. Some linger, some dash ahead, and the separation emerges as bands or peaks at different times. Whether the stationary phase is a solid surface or a liquid coated on a solid, and whether the mobile phase is a gas or a liquid, the principle is the same. Different affinities make different speeds, and different speeds make clean separations. Gas chromatography and liquid chromatography. Volatile components zip at different rates depending on how strongly they stick to the coating and their boiling points. A detector at the end, often a flame ionization detector or mass spectrometer, reports each compound as it arrives. Fast, precise, and sensitive. GC is the quiet hero behind quality control in fuels, fragrances, and forensics. For larger, less volatile, or thermally fragile molecules, liquid chromatography takes over. High-performance liquid chromatography pumps a solvent through a packed column at high pressure, and analytes sort themselves according to polarity, size, or specific binding. Reverse phase columns, non-polar stationary phase, polar mobile phase, separate by hydrophobicity. Normal phase does the opposite. Ion exchange sorts by charge. Size exclusion separates by molecular size. UV or fluorescence detectors watch as each compound exits, and modern systems can even collect fractions for further work. HPLC is the workhorse for pharmaceuticals, proteins, and any compound that would rather not be boiled. Titration, patience and a sharp eye. Titration is chemistry's slow handshake, adding reagent drop by drop until the reaction is just complete. An indicator changes color at the endpoint, signaling that equivalence has arrived, or a pH meter traces the curve electronically. Acid-base titrations find unknown concentrations with gentle precision. Redox titrations follow electron trades. Complexometric titrations use chelators like EDTA to grab metal ions. The arithmetic is simple stoichiometry, dressed up in careful measurement. If one knows the volume and concentration of the titrant and the volume of the unknown's concentration falls out like a solved puzzle. Electrochemical methods. Electrons can be messengers as well as reagents, and electrochemical methods listen to what they say. Potentiometry measures voltage without drawing current. Think of a pH electrode quietly watching proton activity. Voltammetry sweeps potential and measures current, mapping out where oxidation and reduction happen and how fast. Coulometry counts every electron that passes, integrating current over time to find exactly how much substance reacted. These techniques excel at trace metals, redox active organics, and dissolved gases, often with sensitivity that rivals or beats optical methods. Put UV-Vis for concentration, IR for functional groups, NMR for connectivity, mass spec for molecular weight and fragments, X-ray diffraction for atomic positions, fluorescence for glowing signals, chromatography for separation, titration for quantification, and electrochemistry for electron tracking all together, and the analytical chemist has a versatile ensemble. Each instrument speaks a different language, but all describe the same molecular reality. And when their stories agree, confidence blooms like spring flowers after rain. Batteries. Portable chemistry in a can. Batteries are portable chemistry in a can, controlled redox reactions that push electrons through an external circuit, rather than letting them take the short path inside. In a typical cell, oxidation happens at the anode releasing electrons, and reduction happens at the cathode accepting electrons. The electrolyte shuttles ions to keep charge balanced while electrons do useful work outside, powering lights, motors, or processors. The voltage depends on the difference in reduction potentials between the two half reactions, and the capacity depends on how much active material is available. Lithium-ion batteries. Lithium-ion batteries have become the heartbeat of portable electronics because lithium is light and eager to give up an electron, packing high energy into small spaces. During discharge, lithium ions drift from a graphite anode through a liquid organic electrolyte to a metal oxide cathode, often lithium cobalt oxide or lithium iron phosphate. Electrons take the outside route through the device, doing their work. Charging reverses the flow, pulling lithium back into the graphite. The dance can repeat hundreds or thousands of times before capacity fades. Safety matters. Overcharging, overheating, or internal shorts can lead to thermal runaway, so modern packs are laced with sensors and circuitry that watch over the chemistry like attentive guardians. Fuel cells. Fuel cells skip the recharging step by continuously feeding reactants. In a hydrogen fuel cell, hydrogen gas flows to the anode where it splits into protons and electrons. The protons travel through a proton exchange membrane to the cathode. The electrons travel through the external circuit, generating power along the way. At the cathode, oxygen combines with the arriving protons and electrons to form water, the only exhaust. As long as hydrogen and oxygen are supplied, current flows. The catch is hydrogen storage and production. Compressing or liquefying it takes energy, and most hydrogen today comes from natural gas reforming, not from renewable electrolysis. Still, the vision is compelling: electricity from chemistry with water as the only whisper left behind. Electrolysis, running batteries backward. Electrolysis runs batteries backward, using electrical energy to drive non-spontaneous reactions, pass current through brine and chlorine gas bubbles at the anode, while sodium hydroxide accumulates at the cathode, the chloro-Kali process that supplies raw materials for plastics, paper, and water treatment. Electrolyzed water and hydrogen and oxygen emerge, splitting the molecule back into its elemental halves. Electrowinning refines metals like copper by depositing pure metal at the cathode from a solution of ions. Electroplating coats objects with thin, even layers of chrome, gold, or zinc for protection or decoration. In every case, voltage overcomes thermodynamics and electrons become sculptors. Corrosion. Batteries nobody asked for. Corrosion is an unwanted battery where metal acts as the anode, losing electrons and dissolving into ions. Iron rusts when it oxidizes to iron radylose or iron radium, and oxygen or water acts as the cathode, accepting those electrons. Moisture and salt speed the process by conducting ions between anodic and cathodic sites on the same surface. The rust that forms is porous and flakes away, exposing fresh metal underneath in a slow spiral of decay. Prevention strategies interrupt the circuit. Coatings block moisture. Galvanizing sacrifices zinc, which corrodes instead of iron because it's more easily oxidized. And cathodic protection hooks the structure to a sacrificial anode or imposes an external voltage that forces electrons back onto the metal, reversing the natural flow and keeping dissolution at bay. From batteries that bottle redox until we need it to fuel cells that flow continuously, from electrolysis that splits molecules with electrical muscle to corrosion that quietly dismantles what we build. Electrochemistry is electrons in motion doing work, and controlling their path is half engineering, half art. Organic synthesis, precision carpentry with molecules. Organic synthesis is precision carpentry with molecules, cutting here, joining there, protecting one spot while changing another. Retrosynthetic analysis works backward from the target. Identify key bonds, imagine how they might form, and trace back to simpler starting materials until something commercially available appears. Along the way, chemists juggle reactivity, selectivity, and yield, choosing reagents and conditions that coax one transformation without scrambling the rest of the molecule. Protecting groups. Protecting groups are temporary shields. An alcohol might interfere with a nearby reaction, so mask it as a silyl ether or an acetate, something inert under the conditions ahead. After the delicate step is done, remove the protecting group with a reagent that leaves everything else intact. Orthogonal protection schemes let multiple groups be added and removed independently, like managing several locks with different keys. It's extra steps, but the payoff is control, making one change in a crowded molecular neighborhood without waking the neighbors. Transition metal catalysts. Transition metal catalysts have revolutionized bond making. Palladium-catalyzed cross-coupling reactions, Suzuki, Heck, Negishi, Stille, join carbon fragments that once required harsh conditions or circuitous routes. The metal shuttles between oxidation states, picking up one partner, grabbing another, stitching them together, and releasing the product, ready to go again. Metathesis, catalyzed by ruthenium or molybdenum complexes, swaps pieces of double bonds like a molecular square dance, building rings or complex frameworks with elegance. These catalysts work in parts per thousand or even parts per million, turning impossible-looking syntheses into reliable, scalable processes. Green chemistry principles. Green chemistry asks not just can we make it, but can we make it kindly? The 12 principles guide toward less waste, safer reagents, renewable feedstocks, and energy-efficient processes. Use catalytic rather than stoichiometric reagents, designed for degradation so products don't linger. Choose solvents that are benign, or better yet, skip them. Maximize atom economy so most of the starting material ends up in the product rather than in the waste stream. These aren't constraints. They're creative challenges that often lead to cheaper, safer, and more elegant chemistry. Total synthesis of natural products. Total synthesis of natural products is mountaineering with beakers. Taxol, a complex cancer drug isolated from Pacific yew bark, took decades of effort to synthesize in the lab, yet that journey refined techniques now used across pharmaceutical chemistry. Vancomycin, vitamin B2 palytoxin. These molecules have dozens of stereocenters, sensitive functional groups, and rigid scaffolds. Synthesizing them from simple starting materials proves not only that it can be done, but teaches what steps are rate limiting, what shortcuts might exist, and how to think several moves ahead in molecular chess. Combinatorial chemistry. When screening matters as much as synthesis, combinatorial chemistry accelerates the hunt by running many reactions in parallel or pooling intermediates and splitting them to create libraries of related compounds. Chemists can make thousands or millions of variants and quickly test which ones bind a protein, inhibit an enzyme, or light up a sensor. Solid phase synthesis, growing molecules on beads that can be washed, split, and recombined, turns mix and match into an assembly line. It's less about artistry and more about coverage. Cast a wide net and let biology or physics pick the winners. From retrosynthesis that dreams backward through bonds to protecting groups that guard the vulnerable, from metal catalysts that stitch carbon together with finesse to green chemistry that seeks the gentlest path, from Herculean total syntheses that conquer complexity to combinatorial libraries that embrace diversity, organic synthesis blends logic, creativity, and patience into the craft of making molecules that never existed before. Chemistry is the language the universe speaks when atoms meet, when bonds form and break, when energy flows and structure emerges. It's in the breath leaving your lungs right now, in the warmth of your blanket, in the circuits of the device you're holding, and in the enzymes quietly stitching and unstitching molecules as you drift towards sleep. a gentle closing. And so, as the evening deepens and the stars begin their watch overhead, we've wandered through the soft architecture of matter, from the quiet geometry of molecules and the patient folding of proteins, to the rhythms of polymers and the glow of semiconductors, to the invisible cycles that keep air and water moving, and finally to the creative choreography of making new molecules where none existed before. So close your eyes and picture, if you like, a molecule of water, simple, elegant, bent at just the right angle, drifting through a cell, carrying a message or a nutrient, or just being itself. Picture the double helix of DNA, softly unzipping and zipping again as your cells read their instructions. Picture enzymes, folding substrates into their active sites, like gentle hands guiding puzzle pieces into place. Picture the slow, steady exchange of carbon dioxide and oxygen in your lungs, the electron transport chains in your mitochondria lighting up like tiny strings of holiday lights. There's no need to memorize these details tonight. They'll be waiting tomorrow, patient as minerals, steady as stars. For now, let the concepts settle like snow, soft and gradual, covering the landscape of your thoughts in a calm, even layer. Let your mind wander through double bonds and hydrogen bonds, through chiral centers and catalytic cycles, not to master them but simply to visit them, like walking through a moonlit garden where every flower has a story but none demand to be picked. The atoms that make you are ancient, carbon forged in distant stars, oxygen born in stellar fires, hydrogen from the very first moments of the universe. They've traveled unimaginable distances and countless transformations to be here now, arranged in the particular, intricate temporary pattern that is you. And when you sleep, they keep working, repairing, building, communicating, balancing, carrying out 10,000 quiet tasks, so that when morning comes, you can wake refreshed and whole. For now, just breathe. In and out, each breath a partnership between your body and the air, between hemoglobin and oxygen, between chemistry and life. Let that partnership carry you gently into rest. All of this chemistry asks nothing of you right now. It simply continues, reliable and rhythmic as a lullaby hummed by the cosmos itself. If a thought about redox or resonance or polymer chains drifts through your mind, let it pass gently, like a cloud across the moon. There's no test, no urgency, no need to hold on. The science will be there in the morning, patient and welcoming, ready whenever curiosity calls again. Good night. Sleep well. The molecules will keep their watch. May your sleep be deep and restorative. May your dreams be kind. And may you wake tomorrow with the quiet wonder that comes from knowing, even if only in the back of your mind, that you are made of stardust, arranged into consciousness, held together by forces as old as time, and surrounded every moment by the soft, steady magic of chemistry.